Welcome to another deep dive. We've got some really interesting listener-submitted materials today, all about fracture stimulation,
Yeah,
which is, a technique really kind of at the core of how the petroleum industry boosts well production.
it is.
And today we're going to unpack those materials. We're going to pull out the key insights,
Yeah.
help give you a clear understanding of how it all works
Right.
and why it matters. So consider this your shortcut to becoming a mini expert in the art and science of cracking open a formation.
Absolutely. And at the heart of it, fracture stimulation is just about making wells produce better. So we're talking about overcoming damage, whether that's natural damage or induced damage from drilling. It's about unlocking those reserves that might not be economical otherwise. It's about speeding up the rate at which we get oil and gas out of the ground
Yeah.
and even controlling unwanted production like water or solids.
Right. And what's fascinating is that it's not just about brute force. There's this whole intricate dance of economics that has to play into this as well. We have to constantly be evaluating different treatment approaches, always weighing, potential costs against the anticipated revenue. It's a balancing act.
Absolutely.
And, a deep understanding of the financial implications is just as vital as the engineering.
It really is. And there are some great financial lenses that the sources highlight that really help us make these crucial investment decisions, like discount rate, for example.
Hmm.
This accounts for the time value of money,
Yeah.
accounts for the risk involved. And then there's the rate of return, or the profitability index. This basically tells us the compounded interest rate that the investment breaks even at. Now, these aren't just abstract financial concepts.
Right.
These directly influence how much we're willing to invest to stimulate a well. So, for example, if a particular play has high perceived risk,
Yeah.
which would lead to a high discount rate, well, shorter, less capital-intensive treatments with quicker returns might look a lot more attractive than those larger, longer-term investments, even if the latter have higher NPV.
I see. I see. And there's actually a really key trade-off that's highlighted in one of the sources talking about maximizing DROI, that's discounted a rate of return on investment,
Yeah.
versus maximizing NPV. And the source points out that, if you want to maximize DROI, that often points towards smaller, more cost-effective treatments.
Right.
And that makes perfect sense. If you're operating with limited capital, you've got a huge portfolio of wells that need stimulation.
Mm-hmm.
You want to get the most bang for your buck on each investment. You want
Yeah.
the quickest return. However, the source also emphasizes that if capital's not an issue, if you have a really strong portfolio of, promising well candidates, then maximizing NPV becomes that priority,
Right.
which potentially leads to larger, more extensive treatments that unlock greater long-term value.
Yeah, and one of the sources even demonstrates that even with real-world limitations,
Mm-hmm.
like a fixed budget or a finite proppant supply,
Mm-hmm.
that rigorously evaluating different proppant types and concentrations within these constraints is essential to really squeeze out the best possible NPV. It's all about smart optimization.
So smart optimization. So you've navigated this economic landscape.
Yeah.
You've picked your fluid. You've figured out your injection rate.
Mhm.
What are some of the next big levers that you pull when designing a fracture treatment?
So this really brings up an important question about the core design elements.
Oh.
We have the size of the treatment. This is how far we extend the fracture. We've got the proppant type,
Mm-hmm.
those tiny particles that hold the fracture open, and then the proppant schedule. When and how we actually inject that proppant. Now, ideally, the treatment size is dictated by that economic sweet spot we were talking about before. But, as we've
Yeah.
seen
Yeah.
practical things like fixed costs of mobilizing equipment or logistical caps on how much proppant or fluid we can actually handle, those things can define the treatment scale.
Yeah, those practicalities always seem to come into play. Let's actually dig into costs a little bit. When we talk about the total bill
Yeah.
for a fracturing treatment, what are we looking at?
So broadly, we can categorize these costs into variable costs.
Right.
Those that fluctuate with the treatment size, and fixed costs.
Mm-hmm.
Those that remain fairly constant regardless of the size. Now, the variable costs, they're directly linked to the materials
Yeah.
and the energy that we use. So think about the fracturing fluid itself. This includes the base fluid, all those specialized additives, the blending and mixing processes, transporting to the well site, storing it, and then disposing of it.
That's a lot. Yeah, that's a lot of cost centers right there.
And the more fluid you pump,
Yeah.
the more it's going to cost. And then you have proppant. That's a major variable expense as well. You've got the cost of the proppant material itself,
Mm-hmm.
getting it to the well site, storing it, and then the pumping energy. And then there's hydraulic horsepower. This is the sheer power needed to pump all that fluid at very high pressures.
Mm-hmm.
And that cost is directly tied to the injection rate and the surface pressure.
Okay, so those are the things that kind of scale with the treatment. What about fixed costs? What are the costs you can't get away from?
So those are the more constant overhead-like expenses.
Mm-hmm.
Mobilizing all the equipment,
Yeah.
personnel to the well site, the cost of preparing the well itself for the treatment,
Okay.
which may involve a workover rig,
Yeah.
and then the cleanup costs. So things like using coiled tubing to remove debris
Mm-hmm.
and disposing of fluids if that wasn't already included in those variable fluid costs.
Okay, so we've got a good grasp of the costs. How do engineers actually go about this process of designing and optimizing these treatments? What's the general step-by-step approach?
It's really about integrating different pieces of the puzzle.
Yeah.
You need to predict the geometry of the fracture, so how far and wide it extends,
Mm-hmm.
and understand how that fracture impacts production and ultimately the financial return.
Right.
And this often involves using models,
Okay.
ranging from relatively simple analytical equations to more sophisticated 2D and 3D simulations. And the more advanced the models and the better data you feed into them, the more confident you can be
Yeah.
in the optimization. And it's always prudent to run sensitivity studies, tweaking those parameters with the most uncertainty to really see how it affects things.
So what are the initial, kind of foundational steps in the design procedure?
First, you select fracturing fluid systems that are compatible with the specific formation,
Mm-hmm.
right? You have to understand the geology. Then, based on the stresses downhole and the conductivity you need,
Right.
you choose the proppant type.
Mm-hmm. And then is it kind of just pump in, just crank it up and send it down?
Not quite. You got to determine the maximum allowable pump rate. This is often dictated by pressure limitations of the wellhead and the tubulars, those pipes going down.
Mm-hmm.
Finding that optimal injection rate is a balance.
Okay.
Higher rates, they can minimize fluid leak off into the surrounding formation, which is good,
Mm-hmm.
but they also demand more horsepower
Mm-hmm.
and can even lead to sheer degradation of the fluids.
Sheer degradation. Sounds like you're basically damaging the fluid by pumping it.
Exactly. Those mechanical forces at high pump rates can break down the long polymer chains that give the fluid its viscosity,
Okay.
making it less effective at carrying the proppant.
Gotta find that sweet spot.
Yep. After that, you need to select a fracture propagation model,
Mm-hmm.
perhaps a pseudo-3D model that best represents the formation characteristics and the expected pressure response during fracturing. And this choice is informed by data, things like in situ stress measurements, lab tests on core samples, and any calibration treatments or logs.
Okay, so you've got your fluid, you've got your proppant, pump rate, your model.
Mm-hmm.
What's next?
Then we need to feed that geometry model all the input data.
Okay.
This lets us simulate a treatment with a specific size and proppant concentration, see what fracture penetration and conductivity we can achieve.
Mm-hmm.
Alternatively, we can work backwards, use what's called inverse simulation,
Mm-hmm.
and figure out how much fluid and proppant is needed for a desired fracture length and conductivity. Determining the optimal pad fraction here is also really key.
Yeah, we touched on that briefly earlier. Can you explain a little more about the pad fraction and why that initial volume is so important?
Sure. The pad fluid serves several crucial roles. Primarily, it initiates and propagates the fracture, creating the initial width we need for the proppant.
Mm-hmm.
It also helps transport the proppant slurry deeper in. Now, if you use too little pad, you risk proppant bridging
Yeah.
or getting stuck near the wellbore too much, and the proppant might not get carried far enough.
Mm-hmm.
So it's about finding that Goldilocks zone, just the right amount to do both jobs well. And, if your model doesn't account for damage to the proppant pack
Yeah.
from the fracturing fluid itself, you'd also need to factor in a conductivity reduction at this stage.
Okay, so after that initial simulation, what's the next step in the optimization process?
So here's where it gets iterative. You start by incrementally increasing the treatment size, the fracture length, and for each increase, you evaluate the economic outcome. Usually by calculating NPV.
Right.
You keep doing this, simulating larger and larger fractures until the NPV starts to decrease, or you hit a practical limit on length.
So you're basically building this curve that plots NTV against fracture length and trying to find that peak.
Exactly.
Yeah.
Like figure 10-to-1 in one of the sources.
Yeah.
It illustrates that while production keeps increasing with longer fractures, the economic return peaks and starts to decline. And this whole cycle
Mm.
can be repeated for different fluids, proppants, rates, even models to really explore all the scenarios.
Yeah.
And formation permeability and the resulting fracture conductivity,
Yeah.
they're critical here.
Sounds like a lot. Sounds like a lot to keep track of.
It can be.
Yeah.
And as our sources point out, optimizing between different categories of fluids,
Mm-hmm.
oil-based, water-based, foam, that adds another layer.
Right, right.
These fluids are often selected based on compatibility with the reservoir
Mm-hmm.
or their cleanup properties. And quantifying their economic benefits means considering things like formation damage, polymer damage to the pack, and cleanup time. Sometimes a more expensive fluid might lead to better long-term economic performance.
So it's not as simple as just cheapest is best.
Exactly.
Let's zoom in on fracture conductivity.
Okay.
We've said it a lot. It's important. Why? And what influences it?
Conductivity is essentially the ability of that created fracture,
Yeah.
once it's packed with proppant,
Yeah.
to transmit fluids, oil and gas back to the wellbore, fundamental to long-term productivity. And it's influenced by a ton of factors. The proppant itself, its strength, size, roundness, fines content, all these things matter. Then you have the closure stress, that's the pressure squeezing the fracture shut.
Right.
You have damage to the proppant pack caused by the fluids.
Okay.
Polymer damage, the drawdown rate, proppant embedment, and the width of the propped fracture. Chapters 7 and 8 in our sources go into a lot of detail on these factors.
Yeah, and there's that figure 713, I think it was. That really showed how closure stress affects the permeability of those different proppants.
Right.
And it showed that point where you have to move beyond sand to more robust proppants like ISP or bauxite.
Exactly. Once stresses go beyond like 6,000 psi, you start considering ISP.
Yeah.
And above 10,000, those high-strength bauxite proppants become almost essential.
Yeah.
But they come at a higher price, so the economic analysis dictates when their performance justifies the cost. Sand is still the workhorse for lower stresses, cost-effective.
Right.
And resin-coated proppants give you improved crush resistance over sand at a moderate cost increase.
So it's kind of a tiered system,
Yeah.
Depending on what your needs are. You brought up an interesting point. High stress formations don't always necessitate the strongest proppants. Can you explain that?
Sure. So in formations with high permeability, meaning fluids can flow easily through the rock, you might achieve desired production with a small pressure difference between the reservoir and the wellbore. This low drawdown means less stress on the proppant.
Okay.
Plus, reservoir pressure naturally declines with production. So the stress might decrease to a point where even if you increase drawdown later, it won't crush the proppant.
Interesting.
It's counterintuitive, especially in shallower reservoirs,
Yeah.
where high permeability might mean sand is enough,
Okay.
while lower permeability might need those expensive high-strength proppants.
To handle the higher drawdown.
Exactly.
We also saw that relationship in figure 10 too,
Yeah.
between proppant concentration and conductivity.
Right.
More proppant, more conductivity.
Up to a point. As you increase concentration, you build layers of proppant particles, more pathways for flow. But Figure 10.3 shows that beyond a certain point,
Yeah.
like 5 layers for 2040 mesh sand, the proppant pack can become unstable,
I see.
risk of flowback. And in softer formations, the outer layers can embed, reducing the effective flow width. So sometimes you might consider proppant consolidation to bind them together.
Interesting. And it's not just about initial placement.
Right.
Other things can reduce conductivity over time.
Absolutely. Residue from fluids, formation fines, degradation of the proppatent, and mineral scale buildup.
Yeah.
That's why we often design with higher initial concentrations to compensate for those potential losses.
Okay, so you over-engineer it a little bit.
You could say that.
Now, dimensionless fracture conductivity, CFD,
Yeah.
why do we even bother with that?
It's a really useful concept. It lets us compare the effectiveness of different fracture designs on production in a standardized way, regardless of the reservoir.
So a universal yardstick.
Exactly.
Yeah.
By plotting CFD against dimensionless time on type curves, like figure 10:4, you can see how different designs are projected to perform without getting bogged down in specific permeability or viscosity.
So apples to apples?
Precisely.
Yeah.
And that figure also shows how changes in length and proppant volume affect CFD and rate.
Yeah.
So doubling the length without increasing proppant might not improve early production much,
Right.
points A and B on the curve, but increasing proppant to maintain conductivity as you lengthen the fracture, point C, that shows a more substantial increase. Even better gains are often seen by increasing conductivity for a given length,
Okay.
point D. So there's different ways to play with those parameters.
Right. And what about that rule of thumb for optimal CFD?
Yeah, generally a CFD between 10 and 30 is considered a good
But
target.
for a given length.
Right. But the actual benefit above 10 depends on dimensionless time, TD.
Mm-hmm.
If your calculated TD at a certain time, say 36 days, is high, above 0.1,
Yeah.
there's minimal extra production from a CFD much higher than 10.
Okay.
But if TD is very low, then higher CFD could mean big improvements.
I see.
It's all about understanding those relationships.
What about the strategy of using higher permeability proppant? Like bauxite or ISP in the tail end?
Right, so the idea of pumping a high conductivity tail end
Yeah.
is to maximize that long-term productivity,
Okay.
especially near the wellbore, where stresses are highest. You put a stronger proppant there to maintain conductivity and prevent restrictions.
Makes sense.
But figure 10-4 suggests that if the overall CFD is already high and dimensionless time is beyond 0.1, the benefit of that expensive tail end might be small,
Okay.
unless you're really worried about proppant failure or non-Darcy flow.
Right. Non-Darcy flow, that's where things deviate from the ideal.
Exactly.
What is that exactly?
So we've talked about conductivity based on Darcy's law, which assumes a linear relationship between pressure drop and velocity.
Right.
Non-Darcy flow adds another pressure drop, significant at high rates,
Okay.
proportional to velocity squared. This can actually exceed the Darcy pressure drop, especially near the wellbore.
Where those velocities are highest.
Exactly.
So under what conditions do you see those really high velocities?
Well, they occur along the fracture, but they're most pronounced near the wellbore, where flow converges. And the magnitude isn't just about velocity. It's also affected by proppant characteristics, whether it's crushed, how much residual fluid is there, even multi-phase flow can make it worse.
So another layer of complexity.
It is. Because velocity isn't uniform.
Yeah.
And these turbulence factors vary. It's tough to predict the impact accurately. While there are empirical methods,
Right.
often you need simulation for a truly accurate assessment.
Is this another reason to over-engineer conductivity?
Yes, increasing width can reduce non-Darcy effects. Doubling width reduces them by a factor of 4. Sometimes a wider fracture with a less permeable proppant is better than a narrow one with high perm proppant, just to minimize those losses.
Interesting.
But don't just use low perm proppant at high concentrations to get width.
Right.
And in low perm formations, non-Darcy is less of a concern anyway.
Back to proppant selection. What else besides permeability and strength?
It always comes down to economics. Balancing conductivity with cost.
Yeah.
Figure 714 and figure 10-5 show this well.
Yeah.
The proppant with the highest permeability isn't always the best economically.
Right.
You have to consider the total volume needed for a desired conductivity and the cost of that volume. Figure 10-5 compares volumes of different proppants for a given conductivity at different stresses, and figure 10-6 compares the costs.
So those premium proppants, they might be great under high stress, but not so much in lower stress.
Exactly.
Yeah.
The concepts of relative proppant volume and cost help you see this. At high stresses, premiums need less volume,
Yeah.
but they cost more per unit. As stress decreases, their advantage shrinks,
Nice.
and sand becomes a better choice.
So how do you pick the right fluid for the job?
Fluid selection is critical, lots of factors. Compatibility with formation fluids is first, no bad reactions. Then cleanup properties, how easily it's removed. Figure 10-8 gives a guideline for oil and gas wells. The availability and effectiveness of breakers is also key.
Right, to minimize damage.
Exactly. And prior experience in the area plays a role too, for better or worse.
It's interesting, even in high perm formations, damage to the proppant pack from incomplete breakdown can be worse than damage to the matrix.
Yeah, that's important. In those cases, you rely on a conductive fracture to bypass damage. So anything hindering flow through that pack is bad.
So let's dig into viscosity. We know it's essential for carrying the proppant, but what are the challenges?
The fluid's ability to transport proppant often limits how far you can extend the fracture, but viscosity degrades over time and with temperature.
Right.
So we start with a higher viscosity than needed later to ensure transport throughout.
Okay.
That's why we use those cross-linked fluids.
But there are downsides to high viscosity, right?
Definitely. Over-designing due to transport concerns can backfire.
How so?
High polymer concentrations can leave residue, reducing conductivity, and they can cause higher treating pressures, messing with fracture geometry,
Okay.
maybe leading to more height growth than you want.
And sidebar 10B brought up fluid exposure time. What's that all about?
It's a subtle but important point. Lab tests often subject fluid to constant bottom hole temperature.
Mm-hmm.
But in reality, different parts of the fluid experience different times and temperatures.
So the lab is a worst case.
In a way, it can lead to using more polymer than needed.
I see.
Ideally, models should consider this to optimize polymer use.
Okay.
And when determining breaker concentration, consider those temperature profiles.
So higher injection rates, are those always better?
Generally, yes. They increase efficiency by reducing leak-off time.
Mm-hmm.
They can create wider fractures and improve proppant transport due to higher velocities and shorter pumping times.
So less settling and degradation.
Right, but well bore and tubular size can limit rates.
Yeah, practical limits.
And you have to balance the benefits with the increased horsepower costs.
Right.
There's an example where reducing polymer concentration and rate actually led to better height control and improved production. Table 10.1 shows how sensitive height is to injection rate.
So what about geometry modeling? Why is it so important?
It's essential for a few reasons. First, it helps you design that proppant schedule to prevent screenouts.
Yeah.
It also helps determine the fluid and proppant volumes needed for a given penetration.
Right.
And ensures adequate conductivity across the pay zone.
So there are different types of models, right?
Yeah. You have 2D models like PKN, KGD, radial.
Mm-hmm.
These assume constant fracture height. Then 3D models like lumped P3D, discrete cells P3D, planar 3D.
Mm-hmm.
These allow height to vary. And then you have multi-layered models, PKN and P3D, for multiple fractures.
And sidebar 10C has those visuals.
Right.
So how do you choose the right model?
It depends on the complexity, the data, time, and the output you need.
Okay.
P3D models are often a good compromise, commonly used.
Mm-hmm.
Pressure history analysis can also help select the right model
Yeah.
by matching the observed pressure to model predictions. History matching a calibration test is crucial for good design.
And validating the models, how do you know they're right?
Typically, we validate them with well tests and production history matching.
Okay.
But that requires sophisticated analysis and accurate rock properties.
Right.
Layered reservoirs can make this tricky.
What about that design factor, that safety margin?
It accounts for uncertainties and limitations in the models, like unexpected height growth or fluid loss.
Yeah.
By using it, you effectively reduce the target length in your calculations.
So you're being conservative.
In a way, yes. It helps ensure an economic benefit, even with some unfavorable conditions.
Okay. And what about tectonic stress?
Tectonic stresses are those regional stresses in the Earth crust. They can affect the minimum horizontal stress and the correlations we use to estimate Poisson's ratio.
Okay.
If we know the ratio of maximum to minimum horizontal stress, we can incorporate that. It can lead to more accurate Poisson's ratio values.
And that's important for the models.
Exactly.
So now let's get to the actual injection, the proppant scheduling. What are the key things to think about there?
The goal is to create a plan for injecting the fluid and proppant mechium to get the desired penetration, viscosity profile, proppant mass, and conductivity. The proppant addition rate is crucial. You need to manage it carefully to avoid screenouts.
Right, where the proppant plugs up the fracture.
Exactly. Those can be caused by a narrow fracture, pad depletion, or slurry dehydration.
So how has proppant scheduling changed over time?
It used to be based on experience, with gradual increases in proppant concentration. Operators would adjust based on treating pressure.
Okay.
But our understanding has evolved.
Yeah.
Nolte and Smith's work emphasized net fracturing pressure.
Right.
They showed that a rapid pressure increase can indicate a tip screen-out, and that you can often keep pumping proppant even after the fracture stops growing.
Tip screen out, TSO.
Yeah.
That allows you to increase width and conductivity.
Exactly. It's a more efficient way to create that conductive path.
So what's an ideal schedule for a conventional non-TSO treatment?
Ideally, the pad fluid leaks off by the end, and the proppant reaches the tip,
Right.
leaving the whole fracture filled with proppant slurry,
Right.
resulting in uniform width and good conductivity.
And figure 1011 shows some schedules for uniform concentration.
Right.
The ramp-up rate varies with fluid efficiency
Yeah, low efficiency means a more gradual ramp-up.
to make sure the proppant gets to the tip.
Exactly. High efficiency allows a faster ramp-up. But in practice, the early stages are less aggressive to avoid bridging.
And the pad fraction also affects the final proppant distribution.
Absolutely. Too much pad can cause the fracture to keep growing after pumping stops, leading to lower concentration and conductivity.
Okay.
Too little, and you might not get the penetration.
Right.
Or you could even get a premature screen out.
So now let's talk about TSO, which is a bit different.
Yeah.
How does that strategy differ from a conventional treatment?
So in high-perm reservoirs, the goal shifts from length to conductivity.
Because the matrix already flows well?
Right.
So there are techniques for boosting conductivity, bigger proppant, higher concentrations, cleaner fluids, and TSO. And
Yeah.
TSO was a real game changer.
It was.
So what's the core idea behind TSO?
You intentionally create a proppant bridge at the fracture tip,
Okay.
stopping further length growth. But you keep pumping. So the fracture widens, especially near the wellbore,
I see.
and you end up with much higher conductivity than a conventional treatment of the same length.
So it's a more targeted way to get that high conductivity.
Exactly.
There are specific ways to design TSO treatments, right?
Yes, there are. Smith et al. Used a radial flow simulator. Nolte developed analytical relationships based on fluid efficiency and width increase.
Okay.
And Martins et al. Refined this, emphasizing a low concentration stage to avoid near wellbore screenouts.
So it's a true tip screen out.
Right. But whether you use simulators or analytical methods, it's all about managing the pad volume and doing those material balance calculations.
And figure 1015 shows that with evolution after screen out.
Yes, it does.
So how about the Proppant schedule for TSO?
It starts with determining the pad volume based on leak-off.
Okay.
Then you calculate the slurry volume needed for the target width, using efficiency after screen-out. Then you design the schedule, often with a faster ramp-up after the screen-out.
And figure 1016 shows some examples.
Yes.
Figure 1017 compares those final proppant concentration profiles.
Exactly, so you can see the differences.
What about frac and pack?
That's a common completion in unconsolidated sands. It combines fracturing with gravel packing to prevent sand production.
Right, those loose sands can be a problem.
They can. So you fracture, then pack the fracture and annulus with gravel.
Okay.
It requires special tools and techniques, often high slurry concentrations, maybe even TSO.
Interesting.
Figure 1018 shows the improved productivity compared to just gravel packs.
So it's a 2-for-1, stimulation and sand control.
Yes, exactly.
And vertical wells often encounter multiple zones. How do you handle that?
That's when it gets complex.
Yeah.
Ideally, you'd fracture each zone separately, but that's expensive and time-consuming.
Right.
So the goal is to group layers together to minimize treatments.
What about limited entry perforating?
It's used to create a pressure drop across perforations in specific layers to encourage even fluid distribution.
So it overcomes.
Okay, you ready to dive deep? Today we're tackling wellbore completions and perforating and how it all ties into hydraulic fracturing.
Sounds good.
All right, so we've got these really detailed chapters on fracturing operations and well completions.
Okay.
And our mission for this deep dive is to really pull out the core insights about different completion designs and figure out the extra challenges that come up when you're fracturing those deviated and horizontal wells. And then we'll highlight how crucial perforating is to actually getting that good stimulation and making sure you can produce oil and gas, all without overloading you with a bunch of jargon.
Yeah. No textbook reading here.
Exactly.
More like an engaging conversation about, completions and perforating and how it all works.
Exactly.
Yeah.
So to lay it all out, we're going to hit the main completion types.
Okay.
Like, your classic vertical wells.
Yeah.
And then the deviated horizontal, the multiple completions, multiple laterals. We'll cover all that. And then we'll dig into how you isolate different production zones. That's key, right?
Absolutely.
Then the fracturing process itself, especially what you got to do differently for deviated and horizontal wells.
Right.
And then the really cool part, perforating. What are the big parameters that matter? How does it actually affect that fracturing? And then some special techniques that you use.
Okay. Sounds like a plan. Let's get started.
All right, let's do it. So first up, wellbore completions.
Okay.
Our sources, they lay out all these different well designs. You've got your traditional vertical wells, but it goes way beyond that. Deviated wells, horizontal wells, multiple completions in one well, even wells with multiple laterals.
Yeah.
Like branching out. And the first big takeaway here is that choosing the right completion, it's not just about how you drill the well. It's a strategic decision that takes into account how you want to produce from that well and even how you're eventually going to abandon it. Moving to these more complex well designs, it shows a really important idea. A lot of these modern reservoirs, you really got to access more of the formation. to get the most out of it.
Yeah, and it's amazing how much more engineering goes into it. When you move away from just simple vertical wells, like think about deviated wells,
Yeah.
especially when you're going to do hydraulic fracturing.
Mm.
The angle of that wellbore, it really matters. It's not just about reaching a specific spot in the reservoir. That angle directly changes how a fracture is going to start and grow because it interacts with the stresses
Right.
that are already in the rock formation.
And that's where it gets really interesting. When that wellbore isn't lined up with the main stress directions, and a lot of times it's not right.
Right.
Starting a fracture can get tricky. Instead of one clean single fracture,
Yeah.
you might end up with a bunch of little fractures really close to the wellbore, or the fracture might have to twist and turn to finally line up with the stress further out on the rock, what we call tortuosity.
Uh-huh.
And that tortuosity can cause some real problems, Ken.
Yeah, definitely. I mean, you get limited communication between the wellbore and that main fracture. The fracture itself might be too narrow,
Right.
which can cause, proppant to bridge. And then you get those early screen outs. Nobody wants a screen out.
Yeah, that's definitely a bad day.
Yeah, it shuts down the whole operation.
So to get around that, that's why they often suggest an S-shaped completion,
Yeah.
especially in those high permeability reservoirs. The idea is to angle the wellbore out to reach more of the reservoir,
Yeah.
but then curve it back
Yeah.
to be more vertical in that specific zone where you're going to fracture. And this brings up a really important point. In high permeability zones, it's not always about having the longest wellbore possible. It's more about the quality of the connection to the fracture network.
Right. It's like having a super fast internet connection.
Exactly.
You want a clean, direct line, not some long, tangled mess.
That's a great analogy.
Right.
Yeah, so it makes sense that if you're in a low permeability reservoir, a deviated well with just a small section perforated, it might actually be a decent approach.
Yeah.
Because that smaller contact area doesn't matter as much when the rock itself is already restricting the flow. But if you're in that high permeability zone, like we said, the sources they're really pushing for those S-shaped wells, along with perforations that are phased 180 degrees apart and oriented with the fracture plane, or even using slots cut right into the wellbore.
Yeah.
The main goal is to avoid making that already small fracture conductivity even smaller. And they even say that you might need wellbore angles of less than 20 degrees from vertical to get the absolute best fracture geometry.
Yeah, and if you think about it from a production engineering standpoint, the idea is to make the wellbore line up with how you expect the hydraulic fracture to go. So either both vertical or both horizontal.
Right. Makes sense.
And if you go with a horizontal well, then you got another decision to make. Do you want those fractures running along the wellbore? Those are called longitudinal fractures.
Right.
Or do you want transverse fractures?
Right.
The ones that cut across the wellbore.
Right. And if you're going for those transverse fractures in a horizontal well, you're probably going to need to do multiple stimulations along that wellbore. Which brings us to another big topic, zonal isolation.
Yeah, that's critical. You got to make sure each fracture treatment stays in its own zone in that long horizontal well.
It's like trying to water different plants with one hose.
Uh-huh.
You got to find a way to direct that water right where you want it.
Exactly. So with these horizontal and multilateral completions, it sounds like just cranking up the pressure and flow rate isn't enough. There are specific procedures you have to follow, especially to make sure that fracturing treatment is placed exactly where you want it, along that long well bore.
Yeah, and if you're thinking about multiple fractures in a single horizontal well, that zonal isolation for each of those treatments, it becomes absolutely essential. It's non-negotiable.
No way around it.
So how do you actually isolate those zones? Well, our sources, they lay out a few main methods. Cementing the whole liner in the horizontal section is one way. Another is using external casing packers, basically inflatable sleeves around the casing that create a seal. Then there are permanent tools that can be opened and closed to isolate different sections. And finally, you've got retrievable tools that you can run in and out on a work string.
Right, and a lot of times these tools are deployed using coiled tubing, especially in those tricky, deviated horizontal and multilateral wells.
Multilateral completions, those sound even more complex.
They can be, but they can offer so much better drainage and management of the reservoir. Sometimes you might not even need to fracture at all. Yeah, or more likely you might combine multilateral design with some targeted fracturing in certain zones. But the big takeaway here is you absolutely need to plan carefully with these complex completions. They even send us back to a whole chapter on well path design. To highlight the trajectory of the wellbore, you got to engineer it to hit those specific geological units you're after.
That makes sense.
Right.
So it's not just about drilling a hole, it's about drilling the right hole. Now, what about slim hole and monobore completions? Those sound interesting.
Yeah, so the main driver there is cost reduction,
Okay.
trying to cut down the expenses of drilling and completing the well by using smaller casing.
Right, smaller hole, smaller cost.
Mhm.
But are there trade-offs?
Well, the smaller diameter can limit what kind of tools you can use, like specialized stimulation tools, and that can limit your treating pressure during fracturing.
So if you really need a slim hole completion, what do you do?
Well, the sources recommend using heavy-walled tubing as casing. It's strong enough to handle higher pump rates and pressures if you need them.
So it's a bit of a compromise. You save money up front with the smaller hole,
Right.
but you got to compensate with stronger materials to keep those stimulation options open.
Exactly.
Now let's go deeper into zonal isolation.
All right.
Because like we've seen with these horizontal and multilateral wells, it's absolutely essential for getting good stimulation across multiple zones in one well bore. The key is to have those potential producing zones isolated behind the casing with cement.
Right. That way, when you fracture one zone, the pressure and fluids stay put. They don't leak into other zones.
And while we're talking to cement, the sources, they talk about how important it is that the bond between the casing, the cement itself, and the rock formation
Yeah.
stays intact.
Yeah.
They say those tiny channels or microannuli in the cement, they're usually not a big deal during fracturing, especially if the fluid leak-off rate is less than about a gallon per minute. But if you've got big gaps in the cement, that's a problem.
Yeah, for sure. Those big channels, they can let fracturing fluids escape the zone you're targeting. And that could compromise containment.
But here's the thing. The sources say we don't fully understand how those high pressures from fracturing affect the bond between the cement and the casing or the rock.
It's tricky.
It's hard to predict what that cement sheath will look like after fracturing treatment.
Yeah, and a lot of times sonic logs, which we use to check cement bond quality, they show some damage to that bond in fractured zones.
So what are the ways to isolate zones for stimulation?
Well, one way is to do it progressively.
Okay.
Start with the deepest zone, perforate it, fracture it, then plug it off before moving up to the next zone.
And you keep repeating that until you've stimulated all the zones you want.
Exactly. Another option is coiled tubing conveyed treatments, which gives you more flexibility to hit specific zones without working strictly from the bottom up.
Then there are those mechanical bridge plugs, temporary barriers you run in the well on drill pipe or tubing.
Right, and those are usually retrievable, so you can unset them and move them to isolate different zones.
But you can also use wireline set bridge plugs, which are more permanent.
Right, you usually have to drill them out after you're done stimulating.
And those wireline plugs, they're great when you need to isolate multiple zones in a day.
Right.
Or if you don't have a drilling rig over the well all the time.
Right.
What about sand plugs? Those sound different.
Yeah, so after you fracture a zone, you pump a calculated amount of sand downhole on top of the perforated interval. That sand forms a plug, so you can move up and treat the next zone.
Okay.
Once you're done with all the zones, you just circulate the sand plugs out.
And how do you calculate how much sand you need?
Well, that's based on Darcy's law,
Okay.
which describes fluid flow through porous media. It considers things like flow rate, sand permeability, the pressure drop across the plug, fluid viscosity, and how long you want that plug to be.
That's pretty neat.
It is pretty cool.
What about those frac baffles?
So those are special tools that are built right into the casing string, between the producing zones.
So they're down there permanently?
Yeah. So after you fracture the bottom zone, you drop a ball from the surface. That ball lands on the baffle and blocks off any flow below that point. Then you can move up, perforate, and treat the next zone.
And the baffles are designed so you can keep dropping balls to isolate each zone as you move up the wellbore.
Exactly. But you got to make sure those baffle openings get smaller as you go deeper in the well, so the balls seat in the right place.
Makes sense.
But one thing to watch out for is the casing coupling where the baffle is. It can be a weak spot.
Yeah.
And you also got to be mindful of the pressure limits for the system.
Okay. So you got to choose your isolation method carefully, depending on the specific well and the treatment you're planning.
Yeah, for sure.
Now, what if you can't fracture zones from the bottom up?
Then you might use bridge plugs and packers together. The packer seals off the casing, so you can isolate a specific interval.
Okay.
But if you've got open perforations above the packer, proppant from the treatment below could migrate up into the annulus and cause problems.
Oh, I see. That's something to watch out for.
Yeah, definitely.
The sources, they also talk about bridging materials, like rock salt or benzoic acid flakes and ball sealers.
Right. Those can be used to divert fracturing fluids,
Okay.
but they can be a bit unpredictable.
How so?
Well, bridging materials sometimes cause certain fractures to get too much fluid, and ball sealers, their seating efficiency can vary, especially after the perforations have been eroded by all that proppant.
Makes sense.
Right.
Now, what about limited entry treatments? I've heard that term before.
Yeah, so the idea there is to stimulate multiple zones all at once by controlling the pressure drop across the perforations in each zone.
Okay, so instead of isolating each zone, you're trying to treat them all simultaneously.
Exactly. You carefully pick the size and number of perforations in each zone
Right.
to create a pressure difference, usually around 500 to 1,000 psi.
Okay.
And that pressure drop helps distribute the fracturing fluid between the zones.
So it's like a simpler, cheaper way to stimulate multiple zones compared to using all those isolation tools and extra trips in the well.
Right. But there's a catch. If the limited entry treatment isn't designed perfectly, and the number and size of those perforations is crucial,
Right.
you could end up with some zones not getting enough stimulation fluid and proppant. Plus, the sources point out that these designs often don't fully consider the net pressure that builds up in the fracture itself,
Okay.
which can mess up your fluid distribution between the zones.
Right.
Things like the fracture height, the rock stiffness, and how fast the fluid leaks off into the formation. They all matter. And they make it really hard to predict and control where that proppant's going to go.
So limited entry, it sounds good on paper, but it comes with a lot of uncertainty.
Yeah.
You really got to plan carefully and weigh the risks.
Exactly.
Okay, let's move on to perforating.
All right.
It's the step that connects the wellbore to the reservoir,
Mm-hmm.
and it's how we get those fracturing fluids down there.
Mm-hmm.
And the choices you make about the perforating parameter.
Yeah, they have a huge impact on how well that fracturing or matrix stimulation is going to work.
So what are the key parameters?
Well, you've got the size and type of the perforating gun,
Okay.
the type of explosive charge in the gun, shot density,
Right.
which is how many perforations per foot,
Right.
shot phasing. That's the arrangement of the perforations around the casing, the length of the interval you're perforating,
Right.
and even the orientation of the gun relative to where you expect that fracture to go.
Okay, so there's a lot to consider. And if you're doing a frac and pack, where you combine fracturing with a gravel packing for sand control,
Mm-hmm.
the perforating is mostly driven by those gravel packing needs.
Right.
But when the goal is to set up for fracturing, the big thing is to minimize those near wellbore pressure drops.
Yeah. You want to minimize the pressure it takes to pump those fluids in, and also the pressure drop when the oil and gas flows back.
Exactly. And what causes those near wellbore pressure drops?
Well, there's a few things. Friction in the
Mhm.
perforations themselves, those microannulus pinch points we talked about, from the phasing of the gun,
Mhm.
the chance of multiple fractures starting from those closely spaced perforations. Okay.
And even how much that fracture has to twist and turn as it grows away from the wellbore, that tortuosity.
Right. And there are a couple more perforation-related things that can come up.
Yeah, what are those?
Well, one is the integrity of that bond between the cement and the rock face after perforating, whether it's still a good seal, or if you've created leak paths, that microannulus again,
Right.
and then there's the debris left in the perforation after the gun fires.
Yeah, that can be a real problem for matrix acidizing,
Yeah.
where you need those flow paths to be clear.
So for those matrix treatments to work well,
You got to have good communication through as many of the perforations as possible.
right,
And to do that, you can use underbalance perforating.
where the wellbore pressure is lower than the reservoir
No,
pressure.
exactly. Or extreme overbalance perforating, where it's the opposite.
And you can also use ball sealers.
Yeah, those little balls you drop down hole to plug off some of the perforations to make sure the treatment fluid goes into the others for a more even distribution. Interesting. So you're forcing the fluid to go where you want it.
Exactly.
The sources mention that if you don't have enough underbalance during perforating, you can end up with a filter cake of crushed sand outside the perforation when you start pumping fluids.
Okay.
And in some cases, that didn't hurt production, but it did create extra pressure drop during injection.
So underbalance is important, but you got to get it right. Now, what about that bond between the cement and the sand face? Does perforating damage it?
It almost always disrupts it to some degree unless the wellbore is completely full of gas when you perforate.
Okay.
There's a few reasons for that. The gun itself swells when it detonates. The jet from the charge blasts through everything. And those high-pressure gases from the explosion,
Right.
they all contribute. Even the design and phasing of hollow carrier guns can make a difference. The sources, they have some diagrams showing how the cement gets damaged around those perforations.
So what does a perfect perforation look like for hydraulic fracturing? Ideally, you want minimal resistance to flow, a single clean bi-wing fracture, a nice straight path as the fracture grows, and an initiation pressure that's achievable with your equipment.
Makes sense. And to talk about perforation phasing strategies, the sources, they define a vertical well as one with less than 30 degrees deviation from true vertical.
Okay, good to know.
So let's get specific about perforation phasing. For hard rock hydraulic fracturing,
Okay.
start with the simplest case, a vertical well bore with no microannulus,
Right.
that gap between the cement and the formation.
Mm-hmm.
Now, in this case, we're assuming the fracture is going to be vertical.
Makes sense.
So you want a straight shot from the perforation to that growing fracture.
Yeah. But of course, if the fracture isn't vertical,
Mm-hmm.
like near a fault or something, then we
Yeah.
got to consider the recommendations for deviated wells, where you're more likely to have an open microannulus.
Right. So back to our ideal vertical well.
Mm.
For wells producing dry gas, or when the well bore has been swabbed to remove liquids, and when you're using certain perforating guns, like small diameter guns or low shot density hollow carrier guns,
Mm-hmm.
you get a better chance of keeping a good cement bond.
Right.
And if that bond stays intact,
Mm-hmm.
then the fractures have to start from the perforation.
Yeah. No other option.
Now, there's this study that says 180-degree phased perforations
Okay.
placed within 30 degrees of the preferred fracture plane. That gives you good communication and minimizes overlap and tortuosity.
Interesting.
But if that angle gets bigger than 30 degrees,
Uh-huh.
the pressure to start the fracture goes up, and the fracture width near the wellbore goes down.
Mm-hmm.
And if you can't get that 180-degree phasing within 30 degrees, then a 60-degree phase gun might be better. Assuming you only get fractures for the perforations closest to the main fracture plane,
Yeah.
you'd need about 3 times the shot density with the 60-degree gun compared to a 180. You get the same number of connected perforations.
I see. But using that higher shot density with the 60-degree gun, that's probably going to affect that no microannulus assumption we started with.
Right. Good point. The sources, they have a table that shows all the trade-offs for different phased guns. Basically, choosing the right gun depends on what's most important for the specific treatment. Like if you really want to avoid multiple fractures and you're okay with a higher initiation pressure, 180-degree phasing might be best. And no matter what, you got to make sure the casing hole size is big enough for your planned injection rate.
Yeah, you don't want those perforations choking off the flow.
Exactly. Now, they also mentioned using 0-degree phase guns with all the perforations lined up, often at low density,
Uh-huh.
and sometimes with proppant slugs pumped in right after perforating.
Interesting.
The idea is to prevent multiple fractures and screenouts.
Okay.
But the sources, they aren't totally clear on why it works. It could be the low density,
Wow.
or a closed microannulus in those specific wells, or maybe the proppant slugs themselves.
Hard to say for sure.
Right. And they even question whether you actually get a good bi-wing fracture with 0-degree phasing, or if the opposite wing might be restricted. So there's some unknowns there. Now, using low density with 0-degree phasing might help protect that cement bond, while high density with 60-degree phasing could be worse and make those multiple fractures more likely.
It's a balancing act.
It is.
Oh, okay.
Now, what about when you do have an open microannulus in a vertical well,
Okay.
where you still expect vertical fractures?
Uh-huh.
This is common in deviated and horizontal wells because of gravity, no matter what gun you use.
Right.
So that microannulus, it encourages fractures to start from the sand face instead of the perforations,
Okay.
unless those perforations are within about 10 degrees of the fracture plane.
Uh-huh.
But fractures can still start from perforations up to 30 degrees away.
Interesting. So between 10 and 30 degrees, you're more likely to get multiple fractures if there's enough flow in the microannulus. But trying to keep those multiple fractures open, it's tough. They need a lot more pressure. And if the main fracture doesn't start from the perforations, the fluid's going to flow through that microannulus first, which can create pinch points at the fracture entrance
Right.
and make erosion worse. Now, in a normally stressed vertical well, you probably won't have much tortuosity because the fracture will line up with the stress pretty quickly.
That makes sense. The sources, they have another table for this scenario showing the fracture trade-offs for different gun phasings.
Okay.
And if all the factors are equally important, it looks like 120 or 60-degree phased guns are the best choices. 60 might be slightly better for those pinch points,
Mm-hmm.
but it could cause more multiple fractures,
Right.
and you need twice the density compared to 120. Because Only about 1 out of 3 perforations from a 60-degree gun will connect to that main
So you
fracture.
got to weigh the pros and cons.
Always.
Yeah.
Now let's talk deviated and horizontal wells, where we expect vertical fractures, and we're likely to have that open microannulus. In a deviated well, the best fracture geometry is a single bi-wing fracture that extends along the whole perforated section and then gradually turns to line up with the main fracture plane further out.
Right.
So the wellbore is already in the fracture plane. You want 180-degree phased guns oriented up and down.
Mm-hmm.
And this has worked well in deviated wells up to 65 degrees, with those perforations lined up with the minimum stress direction. But if you don't know the stress direction for sure, a vertical up-down orientation is usually a safe bet. And don't forget that casing hole size.
Right, that's always important.
Now, if the wellbore rotates around the fracture plane,
Mm-hmm.
the effective length where the perforations intersect the fracture, it goes down. So in those cases, you want to shorten the perforated interval. Now, for extreme situations, like a horizontal well that's almost perpendicular to the fracture plane
Mm-hmm.
and has a high deviation, over 75 degrees, the recommendation is to cluster those perforations in a short interval, less than 3 feet.
Wow, that's short.
It is. And use max density with multiple phase angles to get the best chance of connecting to a single fracture.
And you need good zonal isolation, too.
Yeah, above and below that short interval.
To make sure one fracture dominates.
Right. And staged fracturing has also been successful in horizontal wells, where the well's perpendicular to the fracture plane.
Okay.
You basically fracture each section one after another, isolating the previous one.
So there's a lot of ways to tackle these complex wells. It just depends on the situation.
It does. Now let's talk about some other proofreading considerations.
Yeah.
Beyond phasing.
Okay, sounds good.
First up, penetration depth.
Mm-hmm.
The sources say you don't really need more than 4 to 6 inches penetration
Okay.
for a good fracture. It usually starts right at the sand face anyway.
Mm-hmm.
So when you're choosing guns for fracturing,
Yeah.
you should focus more on getting the right casing hole size, especially if you're gravel packing. The rule of thumb is the perforation should be at least 6 times the proppant diameter, ideally 8 to 10 times.
Right, to account for proppant size variations. Yeah.
Exactly. And base that size on the smallest proppant in the mix. Now, we talked about limiting the perforated interval in deviated wells to avoid multiple fractures.
Right.
But even in wells that are lined up with the fracture plane,
Uh-huh.
it's often good to limit that interval,
Mm-hmm.
especially in thick reservoirs,
Okay.
because even a little deviation over a long interval.
Uh-huh. Can create a big offset between perforations at the ends.
Right.
And that can lead to multiple fractures.
Exactly. And there are other reasons to limit it too,
Uh-huh.
like getting the right shot density and making sure the flow converges towards the wellbore during production,
Uh-huh.
plus for TSO treatments. Limiting the interval to the middle of the zone helps keep that treatment contained vertically
Okay.
because more of the slurry is exposed to fluid loss
Mm-hmm.
and in formations with big differences in the horizontal stresses.
Uh-huh. A 60-degree phased gun is usually better.
Yeah.
Because it helps line up the perforations with the fracture plane.
Hmm.
If they're not lined up, you need more pressure to start the fracture.
Yeah.
And you can get more pinching near the wellbore.
Okay, that makes sense. Now, shot density and hole diameter, they're tied to the injection rate,
Mm-hmm.
the friction in the perforations,
Mm-hmm.
and the fluid properties.
Right.
There's actually an equation to calculate the pressure drop from friction when you're pumping a non-cross-linked fluid through a perforation.
Mm-hmm.
And a key part of that equation is the discharge coefficient.
Right. Which depends on the shape of the perforation and what kind of fluid you're using. For water-based fluids, it's related to the viscosity.
And unless your gun's perfectly centered in the casing,
Mm-hmm.
the hole size can vary depending on the phasing, meaning different perforations might have different injection rates.
Okay.
You can calculate an average diameter. But service companies, they'll have the specific data for their guns.
Mm.
Plus, during the treatment, the perforation entrance can get rounded from erosion,
Yeah.
which changes that discharge coefficient. And the holes themselves can get bigger
Uh-huh.
from proppant wear and tear. But ultimately, the max rate you can pump is limited by the horsepower you got at the surface
Yeah.
and the max pressure you can handle.
Right. Makes sense.
Now, the number of perforations that actually connect to the fracture, that determines the average flow rate per perforation.
Okay.
For 0 and 180-degree phasing, you can assume they all connect.
Uh-huh.
But for 120, it's about 2/3. And for 60, it's about 1/3.
So you got to factor that in.
You do. And you can adjust the density and diameter to get the injection rate you want
Right.
while managing that friction. Usually you want to minimize it,
Uh-huh.
except for limited entry, where you want that pressure drop across the perforations.
Yeah.
The sources even have an example showing how to calculate the minimum shot density.
That's handy.
Okay, now let's get into frac and pack treatments
Okay.
and high-rate water packs.
Yeah.
These are used in unconsolidated formations to boost production and control sand,
Right.
the perforating in these cases. It's basically the same as for a regular gravel pack.
Uh-huh.
But that way, if your fracture doesn't grow right, you still have that gravel pack to stop the sand.
Like-
And the main goal for perforating in a gravel pack is to maximize that open flow area. But use the smallest holes you can, so the gravel stays put.
Okay.
Fines can really hurt a gravel pack's permeability.
Right.
So you want lots of holes, but not huge ones. You don't want to make the sand unstable.
Gotcha.
60 or even 45-degree phasing is usually best for this. And depending on the rate and pressure drop, you might use those big hole charges at high density, like 12, 16, or 21 shots per foot.
Wow.
Now, these sand-producing formations, they tend to be weak.
Right.
So having a wider fracture and some granulous displacement can actually be good, helps minimize those pinch points near the wellbore,
Okay.
and makes it easier to get that gravel in place. And the ideal scenario is a TSO fracture that packs back into the gravel pack, creating an external pack as well. That's like double the protection. In these cases, things like multiple fractures and tortuosity, they're not really big worries because all that high rate flow in the gravel itself, they tend to erode any restrictions. Now, you typically keep the perforated interval under 100 feet.
Okay.
Ever get that feeling?
Yeah.
Like you're drowning in technical stuff, especially when you're trying to wrap your head around something super complicated.
Oh, yeah. I know that feeling.
Like, I was just thinking about fractured wells. You know,
Yeah.
the way we make those paths underground to get the oil and gas flowing.
Right.
And honestly, it just boggles my mind trying to figure out if those fractures are actually doing what they're supposed to, if they're working, you know.
Yeah.
It's like you need a PhD just to even start understanding it all.
It's a lot, that's for sure. It really is a very complex system, right? You're working deep underground.
Yeah.
And to really get how they perform, you need to look at a whole bunch of different things, like piece it all together.
It's a puzzle.
Yeah.
So for all you listeners out there, we went deep, like really deep, into a chapter about fractured wells, specifically how we check them out, you know, evaluate them after they've been treated. Think of it as a shortcut. We dug through all the details, all the nitty-gritty about how we try to see these fractures, how we measure if they're delivering the oil and gas like they should, and how all of this fits into the whole reservoir picture. We even looked at all the techniques they use to analyze what goes on after the fracturing is done, like a post-mortem almost.
Yeah, yeah.
A fracturing post-mortem.
Exact.
And our goal with this whole deep dive, clarity. We wanted to pull out the really important stuff, the nuggets of wisdom, and make sure you understand the main ways we figure out if a fracturing treatment actually worked.
Right.
And maybe even more importantly, the big things that control how these wells produce over time in the long run, you know?
Yep.
So let's unpack this whole thing. First things first, the big question. How do we even know what these fractures look like? They're way down there underground. It's not like we could just like lower a GoPro or something.
Right.
Or can we?
I mean, in some cases, direct observation, it's an option, but in most cases, we got to get a little more creative. We rely on these indirect techniques. Pretty sophisticated stuff. And these techniques, you can kind of group them. Some look at the wellbore itself, right? Then you got tools for the open sections of the well, and then there are active techniques that we use while the fracturing is happening.
So it's like a multi-pronged approach.
Right.
We're looking at the well itself, we're looking at the open sections, and we're looking at it while it's happening. Okay, so let's start close to home. What kind of information can we gather just from around the well itself?
Well, one of the simpler techniques is just temperature, right? Temperature surveys. When we pump in all that fracturing fluid, it's usually cooler than the rock around it.
Makes sense.
And if you take temperature readings before and after you do the treatment, you can often see a difference.
Interesting.
There will be a change in the temperature profile. You can actually see this conceptually in figure 12.1.
Okay.
So this temperature anomaly, this difference, gives us a basic idea of how far the fracture goes vertically. You know, near the wellbore, sort of a minimum height, you could say.
Oh, okay. So it gives us kind of a baseline.
Yeah. Yeah.
Interesting. What about those radioactive tracers they talk about? It sounds kind of intense.
Yeah, it sounds like something out of a spy movie or something, but they're actually super useful for tracking where the fluid and proppant go.
Okay.
So basically, you add these tiny, tiny amounts of radioactive material to the fluid or to the proppant, or sometimes both.
Okay.
And the proppant, those are those little particles that hold the fracture open.
Right.
So then after the treatment, we run gamma ray logs, and boom, we can see exactly which zones took in that material.
So it's like a little tracker.
Yeah, like a trail of breadcrumbs.
Okay.
And we can get even fancier. You can use different radioactive isotopes for different stages of the fracturing.
Oh, wow.
So you can actually track the whole sequence of events. And figures 12.2 and 12.3, they actually show how this worked, how these gamma ray logs line up with spinner surveys, which tell you where the fluids are being produced.
Wow.
And they use temperature logs too, and all of this together pinpoints the fractured intervals.
So it's like a whole detective kit.
Exactly, yeah.
We're figuring out where it went in, where it's coming out.
Clever. What about density logs? I've heard those mentioned too.
Oh, yeah, density logs. So think of it, well, right.
Yeah.
And it's got those perforations, those holes in the casing.
Yeah.
Density logs, they tell us what kind of fluids are coming out from each of those holes.
Oh, okay.
And when you combine that information with spinner surveys, we get this even clearer picture of what each zone is contributing to the overall production. Now, if you're in an open hole section, where there's no casing, spinner surveys alone can be really helpful in figuring out which layers got stimulated by the fracturing.
Okay, got it. So we've covered the near wellbore stuff. What about when we're in an open hole, that section without the casing? What tools do we have then?
Oh, yeah. So in open holes, we have a few more tricks up our sleeves, to understand what that fracture looks like at the wellbore.
Yeah.
There's this tool called a sonic borehole televiewer.
That sounds fancy. Yeah. So it uses sound waves, acoustics, to create an image of the wellbore wall. And that can reveal fractures, cracks in the rock.
Oh.
But there's a catch, right?
Of course, there's always a catch.
It can be a bit tricky if the borehole shape is irregular, or if the tool isn't perfectly centered, or if the fractures are super narrow, like smaller than the sound waves themselves.
Oh, no.
It's not going to work as well. Like, imagine trying to see these tiny cracks with a blurry ultrasound. It just doesn't give you the whole picture.
So it's like a limitation of the technology, the physics of it all. Okay, so
Yeah.
blurry ultrasound, got it. What else?
Well, then there's the formation microscanner tool.
Yeah.
This one's cool. It uses these tiny electrical sensors, like little buttons that press against the wellbore wall.
Okay.
And by measuring how the electrical resistance changes, we can create a really detailed image of the wall and see where those fractures are and how high they go. And having a survey before the fracturing,
Nice line. Yeah.
that's key. Super important, because then you can see the changes clearly.
Makes sense. Compare and contrast. And what about impression packers? Those sound a bit more old school.
Ah, yeah, impression packers. You're right. They're a bit more old school, more direct, you could say. You've got these inflatable packers, right?
Mm-hmm.
With a rubber sleeve on the outside, a deformable one. And when you inflate it against the wellbore wall, it takes on the shape of the wall, like a mold, a reverse mold.
Mm-hmm. Okay.
And that includes any fractures that are there. So you get an imprint of them.
Like making a Play-Doh imprint, right?
Exactly, yeah, like a Play-Doh imprint of the inside of the well. And these are often run with deviation surveys, so we can also figure out the fracture's orientation. It's azimuth.
Clever. So we've got all these different ways to look at the fracture at the wellbore itself. But what about further out? Like how far does it extend into the rock?
That's where the fun begins. That's when we get into active mapping techniques, stuff we use during the actual injection process.
Real time.
Real time, yeah. And one of the methods is tiltmeter arrays. These are super sensitive instruments. We place them on the surface, believe it or not.
The surface. Wow.
Yeah, on the surface. And they can pick up these tiny, tiny changes in the Earth's tilt, like incredibly small changes.
Wow.
And these changes are caused by the fractures forming down below.
Oh.
So by analyzing these tilts, you can get an idea of the fracture's orientation and potentially how far out it reaches. And figure 12-4 gives you a sense of how this looks.
It's amazing that they can even detect that from the surface. It's like miles underground, right?
Yeah, it is pretty amazing. But it's not always easy.
I bet.
It depends a lot on the depth of the reservoir and the size of the fracture.
Right.
Bigger fractures, shallower depths, easier to pick up the signal. And then you've got all that environmental noise, traffic, wind, rain. All of that can make it tough to isolate those tiny signals from the fracturing.
I can imagine. It's like trying to hear a whisper in a hurricane.
Ex-
So besides the tilt meters, what's the other main active mapping technique? I think it involved like listening for tiny earthquakes or something.
You got it. Triaxial borehole seismics. It's often called microseismic monitoring. And yeah, it's basically like listening for tiny earthquakes.
Tiny earthquakes, okay.
So As the rock breaks during fracturing, it sends out these teeny acoustic waves or seismic waves, and those are the microseisms.
Hmm.
So we put these super sensitive receivers called geophones down in nearby wells, kind of like in figure 12.5.
Okay.
And these geophones, they can pick up these super faint signals.
Yeah.
And by analyzing when those waves arrive and what they look like, we can map out the fracture's orientation, how far it extends laterally, and even if it grows into other layers, above or below our target zone.
So we're basically listening to the rock crack, but on a microscopic level.
Yep, pretty much. And the technology for this, it's come a long way. It used to be just a research tool,
Really?
but now the receivers are way more sensitive
Mm.
and we can process huge amounts of data. So it's much more widely used now. And get this, we can often see not just the final shape of the fracture, but how it actually grows over time, like a time-lapse video almost.
Oh, that's so cool. And the chapter mentioned a big research project, the M-Site project in Colorado. What was that about?
Oh, yeah, the M-Site project, that was a big one. The Gas Research Institute and the U.S. Department of Energy, they funded it. And they used all these sophisticated receivers in these offset wells to capture detailed time-lapse images of how these fractures grow.
Wow.
It was groundbreaking stuff. And figure 12-6, that actually shows the details of one of their treatments in a sandstone formation. They use a lot of gel and sand injected at a pretty high rate.
And what did those images show? What did they learn from all that?
Well, figure 12-7 shows these side view images taken at different times. And at first, when they were just injecting the gel, the fracture didn't really grow much up or down.
Interesting.
Yeah, they think it was because of the stress differences in the surrounding shale layers. Those layers were kind of acting like barriers. Okay. But then when they started adding the proppant, the sand with the fluid, that's when things took off.
It started to grow.
It started growing vertically, yeah. And in the end, you could see it's kind of lopsided, It grew more upwards on both sides of the injection point.
Mm.
And the pressure inside the fracture was going up, so that probably played a role too. Now, figure 12-8, that one gives you a plan view looking down.
Okay.
And you can see the fracture's orientation about north 75 degrees west. But it's important to remember the microseismic image, it's more like an outline, right? It shows you where those tiny seismic events happen, but the actual fracture might be a bit smaller than that.
Oh, okay. So it's like a boundary, the outer limits.
Yeah, exactly.
Fascinating to see how it changes, how it grows, depending on what they're doing with the injection. And the M-Site project, they also used downhole tilt meters, right? How did that fit into the picture?
Oh, yeah, they were pioneers in using those downhole tilt meters, real trailblazers.
Downhole, so not on the surface this time.
Right, downhole. They put an array of them close to the fractured interval in a monitoring well, like in figure 12-9.
Okay.
And they were measuring tilt continuously so they could get data on how the formation was deforming, twisting and turning as that hydraulic fracture opened up. The data is really interesting. You can see how the tilt measurements went up as the fracture opened, peaked when they stopped injecting, and then slowly went down as the fracture started to close.
So they were measuring, what, the strain on the rock almost?
Yeah, kind of like that.
Oh,
Figure 12-10, that shows the tilt measurements at different depths just before they shut the well in. And they've got some modeling results in there, too.
Okay.
And, like we talked about before, in that deep dive on stress and rock mechanics, the tilt pattern near a fracture, it often has this S shape.
Right, right.
Well, they didn't have enough tilt meters to capture the whole S, but they had enough to get a good estimate of the fracture's height and width. And at first, they used simple models, assuming everything was uniform. But then they got fancy and used finite element analyses.
Whoa, fancy.
Yeah, which can take into account all the different rock layers and their properties. And those analyses gave them a much better match. And get this, the modeled fracture height, 67 feet, it was almost spot on with what they saw in the microseismic imaging. And the width, right in line with typical predictions.
So it all lined up. They had the microseismic, they had the tilt meters, it all made sense.
It all came together, yeah.
That's really cool. Okay, so by using all these mapping techniques, the wellbore stuff, the microseismic to the tilt meters, we can get a pretty good idea of what this fracture looks like, its shape and size and all that. But that's mostly about the physical stuff, right?
Yeah.
What about the reservoir itself and how well the fracture can actually move the fluids? Things like permeability and conductivity, right?
Yeah, you're right. That's where pressure transient analysis comes in.
Pressure transient analysis.
Another biggie when it comes to evaluating a fracturing treatment. So we look at how the pressure changes over time, either during production or after we shut the well in. And we can learn a lot from that, a lot about the reservoir rock itself and the characteristics of the fracture.
Okay, so we're talking about pressure buildup, pressure decline, that sort of thing. What were some of the early ideas in this area?
Well, way back like 1937, Muscat did some
A
research.
while ago.
Yeah. And he was looking at steady state flow conditions. That's where the pressure doesn't change over time.
Gotcha.
And later, Van Poelen and Prats, they came along, and they developed models for fractures with different conductivities, some limited, some really high.
Okay.
Prats, in particular, he had some key insights. He introduced this idea of dimensionless fracture conductivity. It's basically a measure of how easily fluids can flow through the fracture compared to the rock around it. And he also came up with this concept of an effective wellbore radius. So if you have a fracture that's super conductive, like it's a perfect pathway, the well acts like it's got a much bigger radius, like half the length of the fracture. You can actually see this in figure 1211.
So it's like the well gets supersized because of the fracture.
Exactly. Yeah, supersize. And then you've got pseudo-steady state flow. That's when the pressure in the whole drainage area is changing, but slowly at the same rate. And McGuire and Sikora, they built this physical model,
Okay.
a potentiometric analog model, they called it.
Tetchy.
Yeah. And their results, you can see them in figure 1212. They gave us a way to estimate how much the well's productivity would go up after fracturing.
Oh, that's useful.
Yeah, really useful. And figure 1213 compares a bunch of early studies in this area. And overall, McGuire and Sikora, their findings seem to be the most reliable for predicting the long-term production increase.
So they were looking at things after the flow had stabilized, basically. What about the initial changes, when you first start or stop production?
That's unsteady state flow or transient flow.
Transient flow.
And it gets more complicated, for sure. Dyes, Prats, Russell, and Truitt, they were some of the first to look into this.
Okay.
And Russell and Truitt, they used simulations, and they found that the same analysis techniques they used for regular wells, the semi-log analysis, it could be used for fractured wells too, but only during that later pseudoradial flow period when the flow starts to look like it's coming from a central point.
Oh, okay. So it kind of reverts back to a simpler pattern eventually.
Right. But before that, it's more complex.
So then they started developing methods specifically for fractured wells,
Yeah,
especially looking at how the fluid flows towards the fracture itself.
you got it. Clark and Milheim and later Sichovich, they showed that during that early period, when the flow is mostly linear, going straight towards the fracture,
Mm-hmm.
well, if you plot the pressure against the square root of time, you get a straight line.
Interesting.
And that gave us a way to analyze that early formation linear flow regime.
Okay, and then Gringarten and Ramy, they're mentioned as being really important in this whole area. What did they do?
Oh, they were huge. They introduced this powerful concept, instantaneous Green's functions, and Newman's product method.
Wow, that's a mouthful.
Yeah, it is. But what it means is they could develop analytical solutions for a whole range of flow scenarios. Uniform flux fractures, infinite conductivity fractures, all sorts of stuff.
So they expanded the toolbox, basically.
Yeah, they really did. And one of their big findings was that the pressure response for an infinite conductivity fracture, you could actually get that from the solution for a uniform flux fracture at a specific point along the fracture.
Okay.
It was a pretty big deal. And this whole Green's function approach, it became a fundamental part of well test analysis for fractured wells.
So they laid the groundwork for a lot of what came after.
Exactly.
Okay, so then researchers started looking at more realistic situations, because not all wells are perfectly vertical, and not all fractures go through the whole reservoir thickness, right?
Exactly. That's when things get even more interesting. Cincolay and his team, they looked at inclined wells and fractures that weren't perfectly aligned with the well bore. Ragavan, he built on Greengarten's work to analyze partially penetrating fractures. And Rodriguez and his colleagues, they made some important contributions too.
So it's all about refining the models, making them more realistic.
Exactly.
But I think the real turning point, the big one, was when they started developing methods for finite conductivity fractures. Right, because let's be real, fractures aren't these perfect superhighways for fluid. they do offer some resistance.
You're absolutely right. That was a major step forward. And Cinquelet and his team, they were at the forefront of this. Their paper in 1978, it gave us a comprehensive solution for how the pressure changes over time in a finite conductivity vertical fracture. And you can see the fracture geometry they used in figure 12 or 14.
Okay.
Then Cinquelet and Samaniego V, they took it even further. They identified all the different flow patterns, the regimes that can happen in these more realistic fractures.
Okay, so let's break those down. What are the key flow regimes we might see in a well with a fracture that's got some resistance to flow?
Well, there are four main ones. You've got fracture storage linear flow, bilinear flow, formation linear flow, and then pseudoradial flow.
Yeah.
And figures 1215, 1216, and 1219, they show you what the flow actually looks like in the reservoir and in the fracture itself for fracture linear flow, bilinear flow, and formation linear flow. It's pretty cool to see it visualized like that.
So these different regimes, they're like the fingerprints of the flow, right?
Mhm.
They tell us what's going on down there. Let's start with the first one, fracture storage linear flow. That sounds like it has to do with the fluid that's actually inside the fracture, right?
Exactly. At the very beginning, if the wellbore effects aren't too strong, the pressure response is all about the fluid expanding inside the fracture itself.
Mm.
And on a log-log plot, pressure versus time, you'll see a straight line with a slope of 1/2.
Gotcha.
But this stage, it's super short, usually. It's often masked by wellbore storage.
Wellbore storage.
Yeah, that's the fluid in the wellbore compressing and expanding. And equation 12 to 8, that describes the pressure behavior during this phase.
Okay.
And equation 12 to 9 gives you an estimate of when it ends, how long it lasts.
Gotcha. Okay, so that's fracture storage linear flow. What about bilinear flow? That one sounds kind of intriguing.
Bilinear flow is really interesting. It's like a 2-for-1 deal.
Okay.
You've got two linear flows happening at the same time.
What?
One in the reservoir rock towards the fracture, and one along the fracture itself towards the wellbore.
So it's flowing both into the fracture and then along it.
Exactly.
Yeah.
Figure 1216, that shows it really well. And this usually happens when the pressure hasn't reached the very tips of the fracture yet. And bilinear flow, it's super important because it's the most direct way to figure out the fracture conductivity, how easily the fluid can flow through it.
Okay, so how do we recognize bilinear flow in the pressure data? What does it look like?
Well, there are a few ways. Equation 1210 describes the pressure behavior. And if you plot the pressure change against the fourth root of time, like on a regular graph, you should see a straight line.
Okay.
And how that line curves later on, whether it goes up or down, tells you if the dimensionless fracture conductivity is above or below about 1.6. Also, if the line doesn't go through the origin, if it's got an intercept, that might mean there's some damage or maybe enhanced permeability near the wellbore. And on a log plot, it'll show up as quarter slopes for both the pressure and the derivative, and they'll be separated by a certain distance related to the logarithm of 4. You can see that in figure 1218. And equation 1211 gives you a rough estimate of when bilinear flow ends, how long it lasts. And the example they give shows how a lower conductivity makes it last longer, which makes sense, right?
Yeah, it takes longer for the pressure to equalize if it's not flowing as easily. Okay, so bilinear flow, that's a key one. Now, formation linear flow, when does that happen?
So formation linear flow, that kicks in when you've got a really high conductivity fracture, dimensionless conductivity above 80, roughly.
Okay.
In those cases, the pressure drop inside the fracture itself, it's basically nothing. So the pressure behavior is mainly controlled by the flow coming straight from the reservoir rock into the fracture.
Okay.
Figure 1219 shows this really well, and the equation for this is 1212. And then equations 1213 and 1214, they give you a rough idea of when it starts and ends. But the important thing is, you won't even see formation linear flow unless the conductivity is high enough.
Got it. So how do we spot formation linear flow in the data?
Well, on a log plot, the derivative curve, it's shifted up a bit by the logarithm of 2. That's figure 1220. And if you plot pressure change versus the square root of time, you should see a straight line. And the slope of that line, it's directly related to the fracture half-length, how far it extends. Figure 1221 shows this, and figure 1222, that one's really helpful. It shows how the conductivity affects the early pressure behavior, how it goes from bilinear to formation linear as the conductivity goes up.
So it's like a visual guide to the different flow regimes.
Exactly.
Okay, and then the last one, pseudoradial flow. That's the one they mentioned all vertically fractured wells might eventually show, right?
Yep, that's the one. So at later times, after all that initial linear flow stuff has settled down, and before the pressure reaches the boundaries of the reservoir, things start to stabilize, and the flow starts to act like it's coming from a regular, unfractured well.
Okay.
But the catch is, the wellbore radius, it's effectively much bigger.
So it's like a supersized wellbore.
Exactly.
It's kind of cool.
Yeah, it is. And the equation for this is 1215. And the dimensionless time when you're using that effective wellbore radius, that's equation 1216. And then equation 1217, that defines how that effective wellbore radius relates to the actual wellbore radius. It's all about this apparent skin effect caused by the fracture. And figure 1224 shows how this skin effect depends on the fracture conductivity. So for high conductivity fractures, the effective radius is basically half the fracture length. But if the conductivity is lower, it depends more on the conductivity itself, not so much on the length.
So even a fractured well, eventually it starts acting like a normal well, just with a much bigger source for the fluids.
Exactly. And this usually kicks in at a dimensionless time of around 3, but it can vary a bit depending on the conductivity.
Okay.
And once you see pseudoradial flow, you can use those classic semilog analysis techniques again, the ones for regular radial flow.
Oh, okay. So it simplifies again eventually. And then even later on, if the reservoir has boundaries, we'll see that pressure hit the edges and it'll be pseudo-steady state flow, right?
You got it. Once the pressure changes have reached all the boundaries, it's boundary-dominated flow, or pseudo-steady state flow. And now the pressure behavior, it depends on a bunch of things. The well, the shape and size of the reservoir, the location of the well in the reservoir, and all the formation properties.
So it gets really complex.
Yeah, it does.
And equation 1218 gives you the dimensionless pressure for a well in the center of a square drainage area. And table 12:1, that has all the shape factors for different reservoir shapes and well locations.
Okay.
And the dimensionless time now, it's referenced to the size of the drainage area. That's equation 1219.
Gotcha.
And they even give you an example of how to calculate the time it takes to reach pseudo-steady state flow.
Okay. So we've got all these nice clean flow regimes, but I know the chapter also talks about some real-world complications, right? Things that can mess up those simple models.
Oh, absolutely. The real world is messy. It's never as perfect as the models. And there are a few big things that can throw a wrench in the works. Non-Darcy flow, for example.
Non-Darcy flow. Okay. What's that all about?
So Darcy's law, right? It's that simple relationship between flow rate and pressure drop.
Mm-hmm.
Well, when the fluid velocity gets really high, Darcy's law doesn't work so well anymore.
Interesting. Why not? Think about it. You got all that fluid squeezing through those tiny spaces in the rock or the proppant pack.
Mm-hmm.
At high speeds, it's not so simple anymore. You start getting inertial effects and maybe even some turbulence.
Okay.
Some people call it turbulent flow, but inertial turbulent flow, that's probably more accurate.
Uh-huh.
And this non-Darcy stuff, it's a big deal in high-rate gas wells and also when the flow converges really fast, like near the wellbore. And Wattenberger and Ramey, they found that non-Darcy flow inside the fracture.
Inside the fracture.
Yeah, inside the fracture. That can actually be more important than in the reservoir rock itself.
Wow, that's counterintuitive.
Yeah.
It is. So basically, when you're producing a lot, especially gas, Darcy's law isn't enough.
Got it. So how do we account for this non-Darcy flow?
Well, Holditch and Morse, they used simulations to study it. But Guppy and his team, they really cracked the code. They came up with a way to quantify how non-Darcy flow makes the fracture conductivity look lower than it actually is. Ever get that feeling, where things just aren't flowing the way they should?
Yeah, I think we've all been there.
Like you're expecting a gusher and all you get is a trickle. It's frustrating, right?
Absolutely, whether it's that morning coffee that just won't brew fast enough
Or in the world we're diving into today, an oil or gas well that's just not producing as much as it should.
That's right, and that's where matrix stimulation comes in, a really key technique for getting those wells back on track and maximizing production.
It's all about unclogging the pipes, essentially.
Exactly. And for a little context, the insights we're going to be drawing on come from a chapter dedicated to Alfred R. Hendrickson, often called the father of modern-day acidizing.
Al Hendrickson, yeah. His work was really groundbreaking, wasn't it?
It was. He really laid the groundwork for much of what we understand about matrix stimulation today. So today, consider this your express lane to understanding a crucial but sometimes complex subject.
Our mission, should we choose to accept it,
is to demystify matrix stimulation, to really get to the core of what it is and why it's such a vital tool in the oil and gas industry.
And we'll try to do it without getting too bogged down in the super technical weeds.
Right. The goal is to equip you with a solid grasp of the fundamentals. So let's start with the basics. What exactly is matrix stimulation?
In the simplest terms, I guess you could say it's like giving a good cleaning.
Well, yeah, that's a good analogy. It involves injecting fluids, either an acid or a solvent, into the wellbore to tackle blockages that are within the formation itself. And a really important point here, this injection happens below the pressure that would fracture the rock.
So it's more of a dissolving or dispersing action rather than breaking the rock apart.
Exactly. And the objective is to either clear out those materials that are hindering the flow of oil and gas in sandstone formations
Or to actually create new pathways in carbonate formations.
right, creating those new channels allows the oil and gas to flow more freely to the wellbore. And here's a statistic that might surprise you.
Hit me with it.
Matrix treatments actually make up a whopping 75 to 80% of all stimulation treatments worldwide.
Wow, that's the vast majority.
It is. But here's the kicker. It only accounts for about 20 to 25% of the total spending on stimulation.
So bang for your buck. Matrix stimulation seems like a pretty good deal.
It absolutely is. It's a highly cost-effective technique, widely used across the industry. And when it's engineered properly, the success rates are really impressive.
How impressive are we talking?
Well, with a properly designed matrix stimulation, you can reasonably expect a success rate exceeding 90%.
90%? That's pretty significant.
It is. You get a substantial potential increase in production for a relatively efficient investment. And often you see results much faster compared to other more intensive methods.
But achieving those kinds of results, it's not just a matter of throwing some fluids down the well and crossing your fingers, right?
Not at all. There's a systematic process involved, a series of crucial steps to ensure success.
So walk us through it. Where do we start? How do you even identify the right wells for this kind of treatment?
Okay, so the first and honestly the most crucial step is pinpointing those wells that are underperforming specifically because of formation damage. You see, it's not enough for a well to simply be falling short of economic goals.
Because that could be due to a whole host of other factors.
Exactly. It could be because of inherent limitations of the reservoir itself. Maybe the pressure is just low across the entire field, or the permeability is poor.
Or there could be mechanical issues within the well.
Absolutely. You could have a failing pump, a tubing size that's too small, any number of things. And matrix stimulation won't address those root causes.
Right, it's not a cure-all.
It's not. So the key is to accurately assess what a well should be able to produce if those near wellbore restrictions weren't there. Then you compare that to what it's actually putting out.
It's like a doctor needing to know what a healthy patient looks like before they can diagnose an illness.
Perfect analogy. And that assessment requires a thorough understanding of the formation's geology and the characteristics of the reservoir fluids.
So it's not just about looking at the production numbers in isolation.
Nope. It's about understanding the bigger picture. Now, there's a quick indicator we use called the productivity index, or PI for short.
Okay, break that down for us.
Simply put, it's the well's flow rate divided by the difference between the average reservoir pressure and the pressure at the bottom of the well when it's flowing.
So you're looking at the relationship between flow and pressure.
Exactly. And if you compare the actual PI of a well to what it should be, based on the characteristics of a healthy well in that formation, it can really raise a red flag.
It's a quick and dirty way to spot potential problems.
It is. But of course, it's not the only tool we use.
We need more detailed analysis, right?
Right. And that comes from things like pressure transient testing, or PTA, and well performance analysis.
So PTA is like a pressure EKG for the well.
That's a great way to put it. It allows engineers to see how the pressure in the reservoir responds to changes in flow rate. And from that, they can actually quantify the degree of formation damage.
And get a better handle on how much improvement they could realistically expect from stimulation.
Precisely. And before we even think about stimulating a well, it's absolutely critical to eliminate any mechanical problems within the wellbore itself.
So you have to make sure the plumbing's working properly before you try to fix anything else.
That's exactly right. Is the artificial lift system functioning as it should? Is the tubing size appropriate for the flow rates? If those are the bottlenecks, a chemical treatment isn't going to help.
You can't boost your internet speed if your router is faulty, right?
Exactly. Now, our source mentions a rule of thumb for identifying potential candidates. If a well's current production rate is less than about 75% of its theoretical potential, it might be worth considering.
75%, that's a good starting
There
point.
is, but it's important to remember that it's just a very general guideline, that theoretical potential doesn't always factor in real-world constraints.
Like the specific equipment being used at the surface.
Right. Things like the production tubing, the separator efficiency, all those things can play a role.
So it's more of a preliminary screening tool.
Exactly. And speaking of screening, it's interesting that expert systems are being used more and more for this initial assessment.
AI stepping in to lend a hand.
Essentially, these computer programs use rules derived from PTA results, or those flow rate ratios we talked about, to determine if a well is a good fit for matrix stimulation. Some even consider potential mechanical issues.
So it helps prioritize which wells are most likely to benefit from treatment.
That's the idea. Now, here's a point that I think is really important and that our source emphasizes. The area immediately surrounding the wellbore, that near wellbore region, plays a huge role in a well's overall productivity.
Outsized impact, you mean?
Exactly. Even a small amount of damage in that area can significantly choke off the flow from the rest of the reservoir.
A bottleneck right at the source.
Exactly. And we quantify that near wellbore damage using something called the skin effect. It's a dimensionless term, often denoted by the letters ES.
A positive skin value means there's damage.
Right. A positive skin value means there's additional pressure drop because of the damage. A negative value, on the other hand, suggests enhanced flow.
Maybe because of natural fractures in the rock.
Exactly. Now, skin effect values can range from 0, which means no damage whatsoever, to well over 100.
Indicating severe damage.
Right. And reducing that skin effect even a little can have a dramatic impact on production. Our source gives an example. If a well has a skin effect of 100, bringing it down to just 10 could increase its productivity sixfold.
That's massive.
It is. Of course, achieving a skin of 0 in a sandstone formation is often unrealistic.
But even a significant reduction can make a world of difference.
Absolutely. And to understand the connection between that skin effect and the physical characteristics of the damaged zone, we use an equation called Hawkins' equation.
Hawkins, like the scientist.
Yep, that's the one.
Right.
This equation relates the skin effect to the reduced permeability in the damaged zone and how far that zone extends from the wellbore.
So it's a way to tie the abstract concept of skin to the actual physical conditions in the well.
Precisely. And as figure 13-2 in our source illustrates, even a thin ring of significantly reduced permeability around the wellbore can act like a serious choke point for the flow.
So even a small area of damage can have big consequences.
That's right.
All right, so let's say we've identified a well that's underperforming, and all signs point to formation damage. What happens next?
Well, the next crucial phase is what we call formation damage characterization. It's essentially detective work.
We've got our suspect, now we need to figure out their MO.
Exactly. It's all about determining the root cause of that impairment and pinpointing its location in the near wellbore region.
Sounds like a multifaceted investigation.
It is. It involves a comprehensive review of all the available information. We're talking about the well's entire production history, any reports from previous workovers, the geological knowledge of the formation, and even the field's overall history.
Looking for any clues that might help explain the problem.
Precisely. And then there's the analysis of any physical material that might have been recovered during those workovers. Any plugging material or debris.
The physical evidence.
Right. And then, of course, we rely on data from pressure tests and well logs.
So pressure tests to pinpoint the location and severity of the dam.
Exactly. And well logs, which give us detailed information about the formation's properties downhole.
It's like putting together a puzzle, using all these different pieces of information.
You got it. And our source also mentions the role of databases and expert systems in this characterization stage.
Those AI assistants again.
Right. They're incredibly helpful for managing and analyzing the massive amounts of data that are generated over a well's lifetime.
Helping to sift through the noise and identify patterns.
Exactly. They can highlight trends, flag unusual readings, and ultimately help narrow down the likely causes of damage.
But our source emphasizes that human expertise is still essential.
Oh, absolutely. The experience and judgment of the engineers interpreting this data, that's irreplaceable.
So it's a combination of human and artificial intelligence.
A perfect partnership. Now, here's something to consider. It's not always a single smoking gun,
You mean there could be multiple types of damage contributing to the problem?
Often that's the case. So the engineers have to consider all the potential culprits when designing a treatment. And that's where a thorough understanding of the well's operational history becomes really valuable.
Because damage can occur at any stage of a well's life, right?
Right. From the initial drilling and cementing operations to the perforating process, even ongoing production can cause damage. Previous interventions, like workovers or stimulations, can also contribute.
So it's a bit of a forensic investigation.
It is. And our source also mentions the use of production logs in this characterization process.
Production logs? What are those?
There's special types of logs that measure the flow rate from different layers within the wellbore.
Ah, so you can see which zones are contributing the most or the least to production.
Exactly. And by analyzing that data, engineers can actually calculate a skin effect for each individual producing interval.
Giving a much more detailed picture of where the flow restrictions are.
Precisely. So we've we've gathered all the evidence, and we have a pretty good idea of what's causing the problem. Now what?
Time to roll up our sleeves and get to work, I guess.
Exactly. We move into the stimulation technique determination phase. This is where we decide how we're going to actually stimulate the well.
And I imagine there are a lot of factors to consider at this stage.
Absolutely. The choice of technique depends on the specific production target we're aiming for, the type of rock formation, any practical limitations at the well site, and even budgetary considerations.
So it's a balancing act.
It is, and our source suggests that the desired production target often plays a big role in the decision.
How so?
Well, let's say, for example, in a sandstone reservoir, our calculations show that reducing the skin effect by 90% would be enough to reach the desired production rate.
So you have a quantifiable goal in mind.
Right. And in that case, matrix stimulation would likely be the most cost-effective and efficient option. Similarly, in a carbonate formation, if a skin effect of, say, megage 2 to megage 3 is deemed sufficient to meet production goals, then matrix acidizing would probably be the way to go.
So the target skin dictates the technique.
To a large extent, yes, but it's not the only factor. Now, if matrix stimulation isn't the right approach, what are the alternatives?
What else is in the toolbox?
Well, in sandstone reservoirs, the main alternative is hydraulic fracturing.
Fracking, as it's often called.
Yes, that involves pumping fluids at very high pressure to create fractures in the rock, which then act as high permeability pathways for the oil and gas.
So you're creating new flow paths rather than just cleaning out existing ones.
Exactly. And in carbonates, besides matrix acidizing, we also have acid fracturing.
Which is kind of a hybrid approach, right?
It is. You create fractures and then use acid to etch channels along those fracture faces, further enhancing their conductivity.
So what's the key difference that helps us decide between matrix stimulation and these fracturing techniques?
The fundamental difference is the injection pressure. Remember, matrix stimulation is always done below the formation's fracture pressure.
Right, no breaking the rock.
Exactly. Fracturing techniques, on the other hand, deliberately exceed that pressure threshold to create those fractures.
So it's a more forceful approach.
It is. Our source also mentions unconsolidated sands.
Unconsolidated, meaning they're not tightly bound together.
Exactly. These formations are prone to sand production if the pressure drawdown, that is, the difference between reservoir pressure and flowing wellbore pressure gets too high.
So you risk pulling sand into the wellbore, which can cause all sorts of problems.
Exactly. In those cases, fracture stimulation might be preferred because it can sometimes achieve the desired rates at a lower drawdown pressure.
Minimizing the risk of sand production?
Right. And then there's the issue of zonal isolation.
Meaning we need to make sure we're stimulating the right zones.
Precisely. If there's a concern that a hydraulic fracture might grow vertically into a zone we don't want to stimulate, matrix stimulation might be the safer choice.
Because it's more localized, it doesn't create those large-scale fractures.
Exactly. So we've picked our RAN, well, we know what's wrong with it, and we've decided matrix stimulation is the right approach. Now what?
Time for treatment design.
Precisely. Now, we need to get into the specifics of the treatment itself.
So what are the main options for non-fracture treatments?
Our source mentions two primary types: wellbore cleanup and matrix stimulation.
Wellbore cleanup, that sounds pretty self-explanatory.
It is. It focuses on removing any blockages that are within the wellbore itself, things like scale or paraffin deposits. But our focus today is on matrix stimulation, which targets the rock formation around the wellbore.
So what does a typical matrix stimulation treatment involve? What kind of fluids are we talking about?
Typically, we inject a sequence of different fluids in a carefully planned order.
A cocktail of chemicals.
You could say that it often starts with a pre-flush.
What's the purpose of that?
Well, the pre-flush is a non-damaging fluid that's used to prepare the formation for the main treatment and to help establish the desired injection rate.
So it's like priming the pump.
Exactly. Then comes the main treating fluid, the one specifically designed to tackle the damage. And finally, we use an overflush to displace the main treating fluid further into the formation.
Making sure it reaches its target.
Right. Now, the selection of that main treating fluid, that's a crucial decision.
It's the star of the show.
It is, and it depends on several factors. The type of rock, the specific type of damage, the well's condition, all those things come into play. Now, these fluids, they generally fall into a few broad categories.
Lay them out for us.
Okay, we have solvents, which are effective against organic deposits like paraffin wax. Then there are oxidizers, which are used to break down polymer-based damage. And then we have scale removers for dissolving mineral scales, things like sulfates or oxides. And then, of course, there are acids.
Acids seem to be the go-to solution for a lot of these problems.
They are. They're used for carbonate and some oxide scales for breaking down certain polymer residues, and they're especially important for stimulating carbonate formations.
By dissolving the rock and creating those flow channels.
Exactly. And then we have a special type of acid called hydrofluoric acid, or HF, which is specifically used to address damage from aluminosilicate minerals.
Primarily clays, right?
Yes. Those are often a problem in sandstone formations.
So it seems like there's a specific acid for every type of damage. But our source mentions that hydrochloric acid, or HCl, and mud acid are the workhorses of matrix stimulation. Why is that?
Well, for a couple of reasons. Firstly, they're effective against a wide range of common damage types. And secondly, they're more readily available and less expensive than some of the more specialized acid formulations.
So it's a practicality thing.
It is. They're often the most practical and economical options.
Now, I'm curious, how do these acids actually work? How do they interact with the rock to improve flow?
Okay, so in carbonate formations, HCl reacts with the main minerals, calcite and dolomite, and essentially dissolves them.
So it's like a chemical etching process.
Exactly. And this dissolution can create what we call wormholes.
Wormholes, those sound interesting.
They are. They're these highly permeable, interconnected channels that can effectively bypass the damaged areas and restore flow.
Like creating a network of express lanes for the oil and gas.
You got it. Now, mud acid, which is a mixture of HCl and HF, works a bit differently in sandstone formations.
So it's a two-pronged attack.
Right. The HF is crucial for reacting with clay minerals and other damaging materials, like drilling mud solids or fine sand particles that have clogged the pores.
So it's more of a cleaning action than a channel-creating action.
Right. Now, with all this talk about acids, there's obviously a concern about compatibility.
Meaning the acid might react with things we don't want it to react with.
Exactly. We have to be very careful about potential reactions with the well's steel casing or with certain minerals in the formation.
Preventing unintended consequences.
Right. For instance, if there's a lot of iron present, either in the formation or the well's tubulars, the spent acid can cause iron hydroxide to precipitate out, which can create new blockages.
Oh, that's not good.
It's not. And then there's the risk of emulsions forming between the acid and the crude oil in the formation.
Oil and water don't mix, as they say.
Exactly. And we also have to worry about asphaltenes, those heavy oil components, precipitating out and forming a sticky sludge that can plug the pores.
So how do they mitigate these risks?
That's where pre-flush fluids come in. They're injected before the main acid treatment to address specific issues.
Like a pre-treatment.
Exactly. For instance, a pre-flush might contain a solvent specifically designed to remove oil from the near wellbore area to prevent emulsions.
Making sure everything's ready for the main treatment.
Right. Or it might be formulated to dissolve existing scale before an HF treatment, as HF can react with those scales and cause problems.
So it's like preparing the canvas before you start painting.
That's a good way to put it. And in some cases, we use an overflush after the main treatment.
What's the purpose of that?
Well, for example, in sandstone HF acidizing, an overflush is important to ensure that any secondary precipitation of reaction products happens further out in the reservoir, away from the wellbore.
So you're pushing the potential problem further away from the well.
Exactly. Now, our source also mentions diverting agents.
Diverting agents, what are those?
They're materials that are used to ensure the treatment fluids are distributed evenly across the different zones of the formation.
So it's about making sure the treatment reaches all the areas where it's needed.
Precisely. You see, formations aren't always uniform. Some zones have higher permeability than others, and those high perm zones, we sometimes call them thief zones, they tend to take in most of the injected fluids.
Leaving the less permeable zones undertreated?
Exactly. So diverting agents are used to temporarily block or reduce the flow into those thief zones.
Forcing the treatment fluids into the areas where they're needed most?
That's the idea. And there are different types of diverters, from solid particles and bridging agents to viscous solutions and even foams.
It's like directing traffic, making sure everything flows smoothly.
Exactly. And on top of all that, there's a whole range of other additives that can be included in the treatment fluids.
It's a veritable chemical cocktail.
It is. These additives can do things like protect the well casing from corrosion, help remove organic deposits, stabilize iron to prevent precipitation, and even slow down the reaction rate of the acid.
Each additive serving a specific purpose.
Right. And then there's the matter of actually designing a pumping schedule, which is a pretty intricate process.
It's like choreographing a complex dance of chemicals.
That's a good analogy.
Yeah.
That's where simulation comes in. Engineers use sophisticated numerical models to predict how the treatment will play out.
This is like a virtual preview of the treatment.
Exactly. They can see how the damage will be removed, how the skin effect will change, and how the pressure will behave throughout the treatment.
Helping to optimize the entire process.
Precisely. And our source highlights 4 different levels of matrix design, from a simple photocopy design where you just repeat a previous treatment to much more advanced geochemical-based designs.
So different levels of sophistication.
Right. And they point out that most treatments still rely on those less sophisticated approaches, which might be one reason why some treatments fail.
They even provide a case history comparing a simpler design to a more sophisticated one.
They do. And the results are pretty telling. The more detailed design, the one that utilized a simulator, led to a significantly better reduction in skin effect and a much higher economic return.
Proving that taking the time to do a proper design pays off.
Absolutely. Now, horizontal wells present unique challenges.
Because of their length, right?
Exactly. Getting a uniform treatment along the entire length of a horizontal well bore, that's a tough nut to crack.
So how do they do it?
Our source contrasts the traditional bullhead technique, where fluids are just pumped in from one end, with the more advanced coiled tubing method.
So coiled tubing allows for more precision.
Exactly. You can place the treatment fluids at specific locations along the well bore and use diverters more effectively.
And they mentioned some successful case studies using foam-based or temporarily cross-linked acid systems as diverters in horizontal wells.
Right. These systems have proven to be quite effective in improving treatment distribution in these challenging wells.
Okay, so we've designed our meticulous treatment strategy. What's next?
Now we move into the execution phase. And as our source emphasizes, proper execution is just as important as a good design.
So it's not just about the plan, it's about the execution.
Exactly. This includes rigorous quality control for all the materials and equipment used on the job.
Dotting the I's and crossing the T's.
You could say that. It involves things like verifying the acid concentration, testing the corrosion inhibitors, and checking the properties of the diverters.
Leaving no room for error.
Precisely. And just as important as the materials is the crew.
The human factor.
Exactly. You need well-trained personnel who understand the techniques and can operate the equipment safely and correctly.
So experience and expertise are essential.
Absolutely. And throughout the treatment, data collection is crucial. We need to monitor things like injection pressures and flow rates.
Keeping tabs on everything in real time.
Right. And that leads us to the final stage, treatment evaluation.
Time to assess the results.
Exactly. And this involves pre-treatment, real-time, and post-treatment assessments.
So it's a continuous process.
It is. Before the treatment, we might run tests like step rate tests to understand the reservoir's characteristics.
So we have a baseline to compare against.
Exactly. And during the treatment, if possible, we try to monitor things like the skin effect evolution in real time.
To see if the treatment is having the desired effect.
Right. And after the treatment, we analyze the well's production performance.
Looking for any signs of improvement.
Exactly. We track production rates, monitor pressures, and sometimes analyze fluid samples. By following this entire process, matrix stimulation becomes an iterative learning experience.
So we learn and improve with each treatment.
That's the goal. It's about constantly refining our techniques to optimize well productivity.
So to wrap up, it's clear that matrix stimulation is a complex and sophisticated process. It's not just a quick fix. It's a carefully planned and executed operation that requires expertise and attention to detail.
Absolutely. And I think the main takeaway is that there's no one-size-fits-all solution. Each well is unique, and the treatment needs to be tailored to the specific conditions and challenges of that well.
It's about understanding the problem before you try to solve it.
Precisely. And by moving beyond those simple cookie-cutter approaches, we can achieve much better results.
It really makes you think, This is such a data-driven and customized approach for individual oil and gas wells. I wonder what other seemingly standardized processes out there could benefit from this kind of thinking. What other industries could we apply this level of detailed analysis and tailored solutions to?
It's a fascinating question. And for our listeners who want to delve deeper into matrix stimulation, there's so much more to explore. The chemistry of different acids, the latest diverting technologies, the challenges of stimulating horizontal wells. It's a whole world unto itself.
Well, thanks for joining us on this deep dive into the world of matrix stimulation. We hope you found it insightful.
And who knows, maybe it'll even spark some new ideas for you in your own field.
Until next time. All right, welcome back to the deep dive. Today we're going deep on something that's honestly pretty crucial in the oil and gas world. Formation damage. You know, those times when a well just doesn't produce the way we expect it to.
Yeah, it's a tricky one, for sure, and a costly one.
Big time. And thankfully you sent over this incredibly detailed chapter all about it. Really dives into why things go wrong down there in the reservoir.
It really is like a detective story, figuring out what's holding back the flow of oil and gas.
Exactly. So think of this deep dive as your guide, helping you decode the mysteries of formation damage. We're going to unpack everything from how to spot the signs of trouble, figure out the culprits, and there can be a lot of those, to the expert strategies for fixing things up. All without, hopefully, getting too bogged down in the technical jargon.
Sounds like a plan.
Okay, so first things first. When we talk about formation damage, what exactly are we talking about?
Well, simply put, it's any kind of blockage in the near wellbore region of the rock, that critical zone around the well where the oil and gas should be flowing freely.
So any blockage, like a clog in a pipe.
Kind of, but it's not always that simple. There's actually a really important distinction to make between what we call true damage and what's called pseudo-damage.
Pseudo-damage, fake damage.
Exactly. Sometimes a well might be underperforming, not because of actual physical blockage in the formation, but because of, say, a design flaw in the well itself, or maybe how it's being operated.
Ah, so it's like a slow internet connection.
Yeah.
It could be your router is actually busted, or it could just be you're on the wrong plan.
Perfect analogy. And knowing the difference is really important because the solutions for a poorly designed well are going to be very different from those for actual damage in the rock.
Right. You wouldn't want to try fixing your internet speed by replacing your router if it's just a plan issue. So when we zoom in on this formation damage, where exactly in the well system are we talking about?
Well, problems can crop up in various places, from the cubing inside the well all the way out to the gravel pack and perforations. But when we're specifically talking formation damage, we're really focused on blockages within the rock matrix itself, right around the wellbore.
Okay, so we're talking about the actual reservoir rock, the porous stuff the oil and gas are trapped in.
That's it.
Now, how do experts even begin to figure out what's going on down there? I mean, it's not like they can just, I don't know, send a mini camera crew down to inspect things.
It's true. It's not that easy. This is where the well's history becomes super important. Think of it like a detective piecing together a case. They have to look at the entire life of the well, dig through all the reports, drilling records, completion data, the performance of nearby wells, any past treatments, everything. It all provides clues about what might be causing the issue.
So it's like a medical history for the well, giving doctors a starting point to figure out what's going wrong. What specific things are they trying to pinpoint during this investigation?
Well, they're looking for the types of damage that might be present. Is it particles blocking the pores? Is it some kind of mineral deposit? Or is it something else entirely? And where exactly is this damage located? How extensive is it? And crucially, how's it affecting the well's production or its ability to take in injected fluids?
Got it. So it's a pretty thorough examination of the well's past.
Yeah.
But then how do they distinguish between real formation damage and those pseudo-skin effects you were talking about earlier?
That's a key step. The chapter talks about skin effect, which is basically a measure of the overall resistance to flow in the well.
Okay.
And this resistance, the skin effect, it's not always because of actual physical damage in the formation. There are mechanical things that can add to the resistance and also things related to the way different fluids like oil, gas, and water move through the system.
Right. I guess it makes sense that different fluids would behave differently down there. So give me some examples of these pseudoskin culprits.
Sure. The chapter lists a whole bunch, actually. On what they call the positive side, meaning they add to the resistance, there are things like limited entry. That's where the way the well was completed actually restricts how much fluid can flow into the wellbore, almost like you've only partially opened a valve.
Okay, I can see how that would create a bottleneck.
Yeah.
What else?
Well, sometimes the wellbore isn't drilled right through the most productive zone in the reservoir. And then there's the perforations, those holes in the casing that allow the oil and gas to flow in. If there aren't enough of them, or they're not long enough, or maybe they're angled the wrong way, that can create extra resistance too.
Ah, so it's like trying to drink through a straw with a bunch of kinks in it.
Exactly. And even things like mechanical restrictions within the well itself, or maybe using the wrong type of pump to lift the fluids to the surface, those can contribute to pseudoskin effects as well. And if the reservoir has thin layers of impermeable rock, like shale, that can block the vertical flow and make it look like there's damage, even when there isn't.
Wow, so it can be really tricky to pinpoint what's actually causing the issue.
Mm.
So much can affect the flow. What about these negative pseudoskin effects you mentioned? What are those?
Yeah, those are kind of interesting. They actually make the well appear to be producing better than it really is.
Oh, how does that happen?
Well, it's more common in deviated wells, those that aren't perfectly vertical. But what's really interesting is that there are effects that change depending on how fast you're producing from the well and also what kind of fluids are flowing.
So the production rate matters.
It can, yeah. If you're producing at a really high rate, you can get turbulent flow, especially in the perforations and even in the formation itself. That creates an extra pressure drop, which looks like damage on the measurements, but it's really just the friction from the fluid moving so fast.
So it's like the faster the river flows, the more turbulent it gets.
Exactly.
Right.
And this tends to be a bigger issue in wells that have gravel packs to control sand production and also in high-rate gas wells.
Okay. Are there any other examples of these flow-related pseudoskin effects?
Oh, yeah, definitely. Sometimes scale, those mineral deposits, can build up around the perforations, basically making the openings smaller and increasing the resistance. Then there are issues related to what's called the bubble point and dew point. In an oil well, if the pressure drops below the bubble point, dissolved gas can come out of solution and form bubbles around the wellbore, making it harder for the oil to flow. It's kind of like when you open a bottle of soda too quickly and it fizzes up. Same concept downhole, but not as refreshing, unfortunately.
And what about the dew point?
Similar idea, but with gas condensate reservoirs. If the pressure falls below the dew point, liquid condensate can form and block the gas flow. It's all about the pressure and temperature conditions changing the behavior of the fluids.
Wow, so much going on down there. I never thought about it being so dynamic. Are there any other mechanical issues besides the ones we talked about earlier that can look like formation damage?
Oh, sure. Think about the production tubing. If that gets collapsed or partially blocked, that's obviously going to restrict flow. Same with the perforations. They can collapse under pressure too. And then there's the cement job.
The cement?
Yeah, the cement behind the casing is supposed to isolate different zones in the well, but if it's not done right, you can get unwanted mixing of fluids, like oil and gas or water and oil. And this mixing can create all sorts of problems. Precipitates can form, you can get emulsions that are tough to break, all sorts of fun stuff.
So it's really a case of everything needing to work in harmony down there.
Absolutely. It's a complex system.
Okay, so let's say they've ruled out all these fake damage scenarios.
Yeah.
Any resistance to flow that's left is probably the real deal, right? The actual formation damage we're trying to understand.
Yeah.
So what are the main culprits behind this real damage? What causes it?
Well, the chapter breaks it down into two main categories: natural damage and induced damage.
Makes sense. Let's start with the natural stuff. What kind of damage occurs just from the act of producing oil and gas?
One of the most common is what's called fines migration. It's these tiny particles within the rock itself, often clays, that can get dislodged by the flowing fluids.
Dislodge, like they break free and start moving around.
Exactly. They get carried along by the oil, gas, and water, and then they can lodge in the smaller pore throats near the wellbore, causing blockages. Imagine it like a traffic jam of microscopic particles clogging up the flow.
Interesting. And it's the clays that are the main problem here.
They're a big one, yeah, especially a type called kaolinite. But it can be other tiny particles too, like silt. And the thing is, these clays can be really reactive.
Reactive? How so?
Well, it depends on the type of clay and where it is in the rock. Some clays actually formed within the pore spaces, and they have a lot of surface area exposed, making them more likely to detach and move around.
Oh, I see. So location matters.
It does. And to identify these different clays, they use all sorts of fancy lab techniques like SEM, which is scanning electron microscopy, and X-ray diffraction.
High-tech stuff. All right, what's another natural damage culprit?
Swelling clays. These are, as the name suggests, clays that swell up when they absorb water. And we're not talking about a little bit of swelling. Some types, like smectite, can increase in volume by up to 600%.
600%. That's insane.
It is, yeah. And if they're in the wrong place, lining the main flow paths for the oil and gas, even a little bit of swelling can cause major blockages. Think of it like a tiny sponge blocking a drain pipe.
Great analogy. So tiny particles on the move in clays swelling up like sponges. What else can cause natural formation damage?
Waterform scales are another big one. These are mineral deposits that precipitate out of the produced water, often because of changes in pressure or temperature or if incompatible waters mix.
Oh yeah, like the scale that builds up in pipes and appliances.
Exactly the same concept, but downhole, and it can cause major headaches. There are all sorts of different scales that can form. Calcium carbonate, calcium sulfate, barium sulfate, iron scales, even chloride and silica scales.
Wow, quite a variety.
Yeah.
What makes them form in the first place?
It's all about the balance of dissolved minerals in the water. Anything that upsets that balance, like pressure drops, temperature changes, the presence of certain gases, or even the type of metal used in the well, can trigger scale formation.
Got it. So we've got moving particles, swelling clays, and mineral deposits. What about organic materials? Can those cause damage?
Oh, definitely. Things like paraffins and asphaltenes, these are heavier hydrocarbon components in the oil, and they can precipitate out if conditions change, like if the temperature drops or the pressure decreases.
So it's like the oil's getting a bit too cold and some of its components start to solidify?
Kind of, yeah. The paraffins are like long chains of carbon and hydrogen, and they can form waxy deposits that clog things up. And the asphaltenes are bigger, more complex molecules, and they can also drop out of solution and cause blockages. And then there's tar, which is basically a heavy, sticky deposit that's loaded with asphaltenes.
So it's not just about the rock itself. The fluids themselves can cause problems too.
For sure.
And you mentioned mixed deposits earlier. What are those?
Oh, yeah. Sometimes you get a combination of organic and inorganic stuff all mixed together. Like, imagine salt crystals embedded in a sticky tar-like matrix. Not something you want to see downhole.
Yuck. And the last natural damage culprit you mentioned was emulsions. Remind me again, what are those?
Emulsions happen when you have two or more liquids that don't normally mix, like oil and water, but they get dispersed together, with one liquid forming tiny droplets within the other. It often happens when there's a lot of agitation or mixing.
Okay. So why are emulsions a problem?
Well, some emulsions will separate out naturally once things settle down, but others can be really stable. And these stable emulsions can really mess with the flow. They can block pore throats, cause pressure drops, and make it a lot harder to produce the oil and gas.
I see. So what makes an emulsion stable like that?
Lots of things, actually. Changes in the chemical film at the interface between the oil and water droplets, the presence of fine particles that get stuck at the interface, electrical charges on the droplets, high viscosity of one of the fluids, even natural surfactant molecules or tiny solids like iron sulfide or clay. It's a complicated mix of factors.
Wow. So even the stability of these emulsions is a complex thing. All right. We've covered the natural causes of formation damage pretty thoroughly. Let's switch gears now and talk about the induced damage. The problems we accidentally create through our own well operations.
Yeah, induced damage is a big one. It basically covers any impairment to the formation that's a direct result of our actions, whether it's drilling, completion, stimulation, or injection operations. We can introduce solids that block the pores, change the wettability of the rock, trigger chemical reactions, even introduce bacteria into the system.
Okay, let's unpack some of that. Let's start with the solids. What kind of particles end up causing blockages?
All sorts. During drilling, the mud we use has solids in it, clays, rock cuttings, weighting agents. If those get into the formation, they can bridge across the pore spaces or pack into the perforations, causing plugging. And it's not just drilling mud. Fluids used during workovers, stimulation treatments, even kill fluids, can contain solids that cause problems.
So it's all about using clean fluids, right? Making sure there's no debris that can get into the formation.
Right. Cleanliness is key. And controlling the size of any particles present is really important too. It's like making sure you're not injecting dirt and sand into a sensitive piece of machinery.
Makes sense. Now, what about changes in wettability?
Wettability is all about how well the rock surface likes to be in contact with oil or water.
Okay.
And this can have a huge effect on how easily the oil and gas can flow through the rock. The problem is some of the fluids we inject, like drilling muds or completion fluids, can change the wettability of the formation.
So it's like changing the stickiness of the surface, making it harder for the oil to move through.
Exactly. And it can really mess with the flow.
Got it. What's next on the list of induced damage culprits?
Chemical reactions. especially those that happen during acid treatments.
Acid treatments. But aren't those supposed to help improve permeability?
They are, but there can be unintended consequences. Acid can react with components in the oil, like asphaltenes or iron, and create these really thick, gunky sludges that are hard to remove.
Oh, so it's like the cure being worse than the disease?
Yeah, sometimes. And it's not just sludges. Acid can also cause unwanted precipitates to form, like iron hydroxide or calcium fluoride, which can plug up the pores. And even some of the additives we put in the acid, like corrosion inhibitors, can leave residues that reduce permeability.
So acid is a powerful tool, but it needs to be used carefully.
Absolutely.
You mentioned iron precipitation and iron-catalyzed sludges specifically. Why are those such a big deal?
Well, iron is pretty common in reservoirs, and when it reacts with acid, it can dissolve and then reprecipitate as iron compounds that are really good at plugging pores. And the dissolved iron can also speed up the reaction between acid and asphaltenes, leading to even more sludge formation. It's a messy situation.
That sounds like it. Now, what about bacteria? How do those tiny critters cause damage?
Bacteria can thrive in all sorts of unexpected places, including deep underground, and they can cause a whole host of problems. Some produce hydrogen sulfide, which is corrosive to well equipment and can also form iron sulfide scale. Others produce ferric hydroxide, a gelatinous precipitate that can block flow. Then you've got slime-forming bacteria, which create biofilms that restrict flow and protect other bacteria. And some bacteria can even eat the polymers we use in drilling and stimulation fluids, creating a biomass that causes plugging.
It's like they're waging a microscopic war on our wells.
Pretty much.
So what other types of induced damage do we need to be aware of?
Water blocks are a problem, especially in low permeability reservoirs. If water gets trapped in the pore spaces, it can be really tough to get it out, and that blocks the flow of oil and gas.
And finally, there are those incompatibility issues with drilling fluids, right?
Yeah, especially oil-based muds. They can create stable emulsions or alter the wettability of the formation. So it's all about choosing the right fluids and making sure they're compatible with the reservoir.
Okay, we've covered a lot of ground here. We've talked about the different ways the formation damage can occur both naturally and as a result of our own actions. Now let's focus on specific well operations and how damage can happen during each. Let's start at the beginning, with drilling.
Okay, so with drilling, one of the biggest risks is mud solids invasion. The drilling mud we use is under pressure, and those solid particles can get forced into the pores of the rock around the wellbore.
And that reduces the permeability, right? Makes it harder for the oil and gas to flow.
Exactly. And several things can make this invasion worse. Larger pore sizes in the rock, fractures, smaller particle size in the mud, slow drilling rates, high mud density, even the scraping action of the drill bit. All of these can increase the amount of solids that get into the formation.
So it's a balancing act to drill efficiently without causing too much damage. What about the liquid part of the drilling mud, the filtrate? Can that cause problems too?
Oh yeah, definitely. Filtrate invasion can be a big deal. It can penetrate much deeper into the formation than the solid particles, and it can cause all sorts of problems. Swelling clays, water blocks, changes in wettability.
And the severity of the damage depends on the type of formation, right?
Absolutely. Some formations are more sensitive than others. High permeability sandstones might see more filtrate invasion, but if the formation water is compatible with the filtrate, it might not be a big deal. But in formations with sensitive clays, low permeability, or those with high water saturation, filtrate invasion can be a major issue.
So it's all about knowing your reservoir.
For sure. And using the right drilling fluids. Water-based muds, oil-based muds, polymer-based muds, they all have their own pros and cons, and you have to choose the right one based on the specific formation you're drilling.
Got it. Okay, let's move on to cementing. How can that operation lead to formation damage?
Well, the cementing process itself is relatively short compared to drilling, but it's not without its risks. The washes and spacers used before and after cementing can cause problems if they're not compatible with the cement or if they cause a lot of fluid loss into the formation.
And what about the cement slurry itself?
The high pH of the cement slurry can damage clay minerals in the formation. The calcium in the cement can react with formation brines and create precipitates that block pores. And if the cement slurry is over-dispersed, it can lead to too much free water invasion and water blocks. Plus, if you lose cement into fractures in the pay zone, that's a major problem.
It sounds like cementing is a crucial step, not just for the structural integrity of the well, but also for protecting the formation.
It is, definitely.
All right, let's move on to perforating. This is where they blast holes in the casing to let the oil and gas flow in, right? How can that cause damage?
Well, Perforating, by its very nature, is going to cause some damage to the formation around the perforation tunnels. Even with a slight overbalance in pressure, the jetting action can force debris into the perforations and reduce permeability.
So it's unavoidable.
Pretty much. And using fluids during perforating that aren't perfectly clean can make it worse.
Hmm.
Also, if the perforations aren't deep enough, they might not bypass any drilling damage that's already there. And getting the pressure right during perforating is critical. Too much underbalance, and you could get sand production. Not enough. And the damage might not be cleaned out effectively.
Sounds like a delicate operation.
It is. And you also need to make sure you have enough perforations. Too few. And you're just restricting the flow.
Got it. Now, what about gravel packing? How can that go wrong and cause damage?
Gravel packs are designed to prevent sand from entering the wellbore, but they can become damaged themselves over time. Improper placement of the gravel, leaving perforations uncovered or gaps in the annulus can lead to problems. And if the fluids used to carry the gravel aren't fully cleaned out, or if formation debris is left behind, that can plug up the gravel pack.
So cleanliness is key again.
It always is. And you have to use the right size gravel and the right type of screens. Too large, and fines can get through and cause problems elsewhere. Too small, and the screens themselves can get plugged.
All right, what about workovers? Those maintenance jobs on existing wells. How can those induce formation damage?
Workover fluids can cause many of the same problems as drilling fluids. Plugging by solids, filtrate invasion, emulsion formation, scale precipitation. So it's really important to use clean, filtered fluids and to be careful about placement.
I'm sensing a theme here.
Haha, yes, cleanliness and compatibility. Always. And controlling fluid loss is crucial too. Sometimes they even use special fluids, like foams or mists, to minimize the amount of liquid filtrate that gets into the formation.
Interesting. Now, let's talk about stimulation and remedial treatments.
Yeah.
These are designed to improve well performance, so it seems counterintuitive that they could cause damage. How does that happen?
Well, it's all about the details. If these treatments aren't designed and executed perfectly, they can backfire. For example, when you're cleaning the wellbore, if you dissolve deposits in the tubing, those dissolved materials can reprecipitate in the formation and cause blockages.
Oh, so you're just moving the problem.
Yeah, essentially. And acid treatments, while they can be very effective, come with a whole list of potential risks. Sludges, precipitates, deconsolidation of the rock, damage to proppants or gravel packs.
It's like a delicate surgery, to be very precise.
Exactly, and fracture treatments have their own set of challenges. You can get damage within the proppant pack or damage to the fracture face from fluid leak-off, and even after a treatment, if you don't recover all the injected fluids, those can cause problems too.
So it's not as simple as just pumping stuff down there and hoping for the best.
Not at all.
What about normal production operations? Can those induce damage over time?
Absolutely. In unconsolidated formations, high production rates or changes in water salinity can mobilize fines and cause plugging. Excessive drawdown pressure can lead to sand production or compaction. In fractured wells, high drawdown can even cause the rock to break apart. And pressure and temperature changes during production can trigger scale formation or organic deposition. It's a constant battle.
Wow, so even just producing the oil and gas can be a delicate process. All right, let's shift gears now and talk about the lab. How do the experts in the lab help us figure out what's going on and what to do about it?
The lab is crucial. They do all sorts of tests to identify the damage mechanisms and to evaluate potential treatments. They analyze core samples, produce fluids, any solid deposits they can get their hands on.
What kind of tests are we talking about?
Well, they look at the mineral makeup of the rock, the formation's wettability, the porosity and permeability. They analyze the brine to see if it's likely to form scale, and they analyze the oil to see its potential to form deposits.
So they're getting a full picture of both the rock and the fluids.
Exactly. And then they use this information to test different treatments. They do solubility tests, compatibility tests, core flow tests. They try to recreate the downhole conditions in the lab to see how different fluids will behave.
It's like a dress rehearsal for the real thing.
Exactly.
Okay, so based on this detailed understanding, what are some of the general strategies for addressing different types of formation damage? Let's start with fines and clays.
For fines, the main strategies are prevention, meaning stabilizing the clays so they don't move in the first place, or removal if they've already caused blockages. Mud acids are often used to dissolve clays and dislodge fines. Sometimes they use specialized acids to stabilize the clays. And in some cases, fracturing is the best option to bypass the damaged zone.
What about swelling clays?
Similar approach, often using HF or fluoroboric acid. Again, fracturing might be the only option for deep damage.
And what about unconsolidated formations, where the sand itself is moving?
Those are trickier. You have to be careful not to further destabilize the formation with the treatment fluids. Strategies often focus on reducing the flow velocity near the wellbore, using techniques like tip screen out fracturing or gravel packing.
Okay, what about scales?
Scale removal depends a lot on the type of scale. HCl works well for calcium carbonate. Calcium sulfate might need converters or chelating agents. Barium sulfate and strontium sulfate are tough to remove chemically and often require mechanical methods, and so on. It's a whole chemistry set.
Sounds like it. What about organic deposits?
For paraffins, they use heat, scraping tools, or solvents. For asphaltenes, aromatic solvents are the go-to, often with dispersants. And for mixed deposits, they might use a dual solvent system.
And emulsions?
Mutual solvents are often used to break down emulsions. And for bacterial problems, they use a combination of biocides, oxidizing agents, and acid.
So lots of different tools in the toolbox.
That's right.
Well, this has been a truly deep dive into the world of formation damage. It's clear that this is a complex issue with a lot of different causes and potential solutions.
It is, and it's a constant challenge for the industry.
So what are the key takeaways here? What should people be thinking about?
Well, first of all, recognize that not every drop in production is due to actual formation damage. Sometimes it's a design issue or an operational issue. So the first step is always to diagnose the problem correctly.
Right. Don't jump to conclusions.
Exactly. And then be aware of all the different ways that formation damage can occur, both naturally and because of our own actions. And finally, remember that the lab plays a critical role in identifying damage and testing treatments. It's all about a thorough understanding of the reservoir and a carefully planned approach.
Excellent points. Any final thoughts?
Yeah, just a thought to ponder. As we move towards maximizing production from existing wells and developing more unconventional resources, understanding and mitigating formation damage is going to become even more critical. It's a challenge, but it's also an opportunity for innovation.
A great point to end on. Thanks for joining us on the Deep Dive. We'll see you next time. All right, welcome to the Deep Dive. Today, we're going to kind of get into, well, it's something you might not think about every day, but it's the stuff that gets pumped down oil and gas wells during treatments, right? Specifically when we acidize them.
Right.
And it might, on the surface, it might sound pretty simple. Just pour some acid down the hole, right?
Yeah.
But the chemistry behind making these treatments actually work.
Right.
And not, really importantly, preventing a whole bunch of problems is surprisingly complex.
It is, yeah.
We've got a ton of sources here today, and it really gets into how much thought and precision goes into these processes.
That's right, yeah. It's amazing when you actually look at the sheer variety of components that go into these fluids. And they're carefully chosen and combined to achieve a very specific outcome, thousands of feet underground.
Right.
Each additive has a particular role to play, and understanding those roles is really key to a successful treatment.
Absolutely.
Yeah.
Our sources today give us this detailed look at all these different additives, what their jobs are, how they interact with the well itself, and even the potential knock-on effects that we can see all the way back up at the surface. So our mission today, our deep dive mission, is actually really straightforward. We want to extract those essential insights about these additives.
Right.
So you can really understand why they're so vital, and what can actually happen if they're not selected properly.
Yeah.
So, why is getting the fluid selection and these additives exactly right so important in the first place?
So proper fluid selection is absolutely the foundation of a successful matrix treatment. I like to think about it like a doctor diagnosing a patient before they go and prescribe any kind of medication. And our materials illustrate this really well, just showing all the different types of damage that can occur in a well. Things like emulsions, where the oil and the water just refuse to separate. Changes in the rock's kind of preference for oil or water.
Okay.
We call that wettability.
Yeah.
Water blocks that just prevent flow. Various kinds of scale buildup, organic deposits that kind of gum things up.
Right.
And even tiny silts and clays that can just clog up the pore spaces in the rock.
Right.
And for each of these, there's a specific type of treatment that is designed to address it.
So it's not just one size fits all.
No, definitely not.
Right. It's like, all right, well, what's the problem and what do we need to do to fix it?
Right. And the main treating fluid itself
Huh.
is designed to tackle, the primary damage.
Right.
But as we're going to see, it's the additives that
Sure.
really, step in to prevent this whole range of other potential issues.
So the additives are the workhorses.
They are.
Right. They're like,
They're the specialists.
Okay.
They come in and they take care of all the fine details.
they fine tune everything. So what are these additives doing? Like, what are their actual functions?
So they have this multitude of crucial functions.
Okay.
One of the big ones is to prevent corrosion.
Okay.
We're pumping acid downhole, and that can eat away at our metal components, our drill pipe, our tubing.
Makes sense.
So these additives are there to protect that.
Okay.
Another thing they do is stop the formation of sludges and emulsions. You don't want these gunky mixtures forming downhole, so they help with that.
Okay.
Another thing, iron.
Iron.
So iron, if it's dissolved in the acid, can precipitate out
Okay.
and create blockages. So we need additives to control that.
Okay.
They also improve how easily the well cleans up after the treatment.
Okay.
You want everything to flow back smoothly.
Right.
And they ensure that the treating fluid reaches, all the areas that it's supposed to.
So they improve coverage.
Exactly. Yeah. They make sure the treatment goes where it needs to go.
Okay.
And they can even prevent the precipitation of reaction products.
Oh, interesting.
Sometimes the reaction products themselves can cause problems.
Okay.
And the additives can help mitigate that.
So they're doing a lot.
They are, yeah. They're busy little molecules.
Yeah.
They're multitaskers.
And they're not just used during, the actual treatment, are they?
Right.
I see them mentioned also as pre-flushes and over-flushes.
Yeah, that's a good point.
What's the thinking behind that?
So in pre-flushes, they can actually be used to stabilize some of the more sensitive clay formations before the main acid even comes into contact with them.
Okay.
It's kind of like, preparing the ground before you build a house. You want to make sure the foundation is solid.
Right.
And then in overflushes, they might be used to disperse heavier hydrocarbons, things like paraffins and asphaltenes, that could potentially solidify and cause problems later on.
So they're almost like a cleanup crew.
In a way.
Right. Making sure everything is tidy and flowing properly afterwards.
Exactly. Yeah.
Now, I've seen some really interesting stuff in the sources about how these additives interact with the formation itself.
Yeah, it's fascinating.
Right. And this guy Schechter, 1992, he really emphasizes the importance of the chemical properties of the rock materials.
Yeah, he's a legend in the field, Schechter. And he really highlighted how, it's not just about pumping acid down there. It's about understanding how that acid is going to react with the rock itself.
Okay, and clays?
Yes.
Clays get a special mention, right?
They do.
Because of their huge surface area and their electrical charge.
Yeah, even though clays, might not make up a huge percentage of the rock volume.
Okay.
Their microscopic structure gives them this enormous surface area. It's kind of like, think about a sponge.
Okay.
Right? It's got all those little holes and channels.
Right.
So there's a lot of surface area for things to interact with. Yeah. And the electrical charge on those clay surfaces, even though it's, relatively small, due to these tiny little substitutions within the mineral structure, it plays this surprisingly big role in how they behave when they're exposed to different fluids.
So charge matters.
Charge definitely matters.
Okay. All right. Well, I came across something about silicon and aluminum oxides being amphoteric.
Right.
And this concept of a point of zero charge. Can you break those down for me in a way that makes sense?
So what's really fascinating here is that silicon and aluminum oxides are the main components of sandstones and clays.
Okay.
And they are what we call amphoteric, meaning they can act as both an acid and a base, depending on the conditions that they're in. So their surface electrical charge actually changes based on the pH of the solution that they're in.
Interesting.
It's like think of it like a chameleon changing colors to match its surroundings.
Right.
As the pH increases, the surface charge shifts from positive to negative.
Okay.
And that specific pH value, where the surface charge is exactly 0, where it's neutral, that's what we call the point of zero charge, or PCC.
Right. CC.
PCC. And our materials actually give some examples of this in a table for common reservoir materials, things like quartz, corundum, hematite,
Okay.
calcite, kaolinite, montmorillonite, albite.
Right, and they all have their own
They do, yeah.
PVC values.
Different minerals have different PCC values.
Okay.
And that really influences how they behave.
Okay. So what does all this talk about charge actually mean then when we're, talking about pumping acid down into a sandstone formation?
So if we connect this to the big picture of matrix acidizing in sandstones, the acid we typically use has a pH that's usually below the PCC of most of the minerals in the formation.
Okay.
Which means that under those acidic conditions, the rock materials tend to carry a positive electrical charge.
Okay.
And that is super important because it directly influences how our additives are going to behave.
Right.
Whether they're going to be attracted to the reservoir rock
Okay.
or repelled by it.
Gotcha.
It's all about those interactions.
Okay. So with all these potential complications
Yeah.
and interactions down there,
Yeah.
I mean, where do we even begin when we're talking about selecting the right additives for an acid treatment?
So if we're talking about acid treatments, the critical role of corrosion inhibitors cannot be overstated.
Okay.
They are often considered the single most important type of additive in these scenarios.
Corrosion.
Corrosion. Yeah.
Because we're pumping acid through metal pipes.
Yeah.
So we need something to protect those.
We need something to protect our infrastructure, yeah. So these inhibitors, their main job is to slow down that acid's attack on the metal components.
All right.
The drill pipe, the tubing, all of that.
Okay.
And there's a really nice simplified diagram in our materials that shows how metal corrosion occurs in water-based solutions.
Okay.
It's all about the formation of these tiny little electrochemical cells on the metal surface.
Right.
With areas acting as anodes and cathodes.
Yeah, anodes and cathodes, right? And this is where things get interesting.
Right.
Okay, so what's actually happening at these, anodic and cathodic sites when the acid is involved?
So in acid corrosion on steel, the hydrogen ions that are released by the acid, they're the main culprits.
Okay.
At the anerbic sites, you have the iron in the metal. It loses electrons.
Okay.
And dissolves into the solution as iron ions.
All right.
That's the oxidation part of the process.
Uh-huh.
At the same time, at the cathodic sites, those hydrogen ions, they gain electrons.
Okay.
And they form hydrogen gas. So the metal's being dissolved and hydrogen gas is being produced as a byproduct.
So we're eating away at the metal and creating gas.
Yeah, and that's not what we want.
Not ideal.
Not ideal.
So how do we even measure the amount of damage that's happening?
So the standard way to measure corrosion is in terms of metal loss per unit surface area.
Okay.
Typically pounds per square foot or pound BM/FT2.
All right.
And our materials actually provide these acceptable corrosion limits for low alloy steel.
Okay.
Based on the temperature and how long the metal is exposed.
Okay.
And what's interesting is that higher temperatures can sometimes lead to a more uniform type of corrosion, which can actually reduce the risk of localized pitting.
Oh, so it's not just the total amount of metal lost, but it's also how it's lost.
Right.
Like, is it spread out or is it concentrated in one spot?
Exactly.
Right.
Yeah. And it's all about understanding how the corrosion is occurring.
Okay.
And the effectiveness of the inhibitor
Right.
is not universal. It depends on the specific type of metal alloy that's being used in the well.
Okay.
And some of the older studies that we have really highlight that different inhibitors perform very differently on steels with varying compositions.
Okay.
And this really underscores the need to choose an inhibitor that is specifically suited to the type of steel that you have in your well.
Okay.
And they even point out that just looking at the API steel grade designation, which mainly tells you about the steel's strength, isn't enough to predict how it's going to corrode. The detailed chemical composition of the steel is the real key factor.
Gotcha.
So it's really important to test these inhibitors using actual samples of the metal.
Makes sense.
That's going to be used in the well. And that's why lab testing is so crucial.
You mentioned pitting corrosion earlier.
Yeah.
And that sounds like a particularly nasty problem even in, inhibited acids.
It is, yeah.
Why does that happen?
So pitting corrosion, where you have these localized areas of attack, can be a significant issue, even when you're using corrosion inhibitors. And it can happen for for a few different reasons.
Okay.
The inhibitor itself might break down, become less effective over time.
Okay.
You might not be using a high enough concentration of inhibitor to fully protect the metal surface. Or there could be imperfections or impurities within the metal itself. Like slag inclusions or areas that weren't properly heat treated.
Right. So just little defects in the metal itself can cause problems?
Can cause problems, yeah.
All right. And then there's hydrogen embrittlement.
Yeah.
Which sounds, concerning.
It is concerning. So hydrogen embrittlement is a consequence of that cathodic reaction. Where hydrogen ions are converted into hydrogen gas. And some of that atomic hydrogen can actually be absorbed by the metal itself. And that can lead to a loss of ductility, making the metal brittle and more likely to crack or fail under stress. And certain grades of steel that are used in well construction, like N80, P110, Q125, those are particularly susceptible to this. So selecting a corrosion inhibitor that minimizes hydrogen evolution is crucial.
So it sounds like not all acids are equally aggressive.
No, they're not.
When it comes to corrosion.
No, they're not.
Like some are worse than others. So are there ones that we try to avoid using?
So the corrosivity of an acid depends largely on how readily it releases hydrogen ions in solution. We call that its hydrogen ion activity. And the more hydrogen ions that are available, the more corrosive the acid tends to be. So generally speaking, hydrochloric acid or HCl is the most aggressive of the commonly used acids. Followed by formic acid. And then acetic acid is the least corrosive of those three. So, the more aggressive the acid, the more challenging it can be to inhibit effectively. So sometimes you might have to use a combination of different inhibitors or adjust the treatment design itself.
So what are the main types of corrosion inhibitors that we use when we're acidizing?
So we primarily rely on two main categories. Inorganic and organic inhibitors. And then there's also this class of compounds called inhibitor aids that help boost the performance of the organic ones.
So let's start with inorganic inhibitors. What are they all about?
So inorganic inhibitors are typically salts of metals. Things like zinc, nickel, copper, arsenic, antimony. Historically, compounds containing arsenic have been quite widely used. They work by forming a protective layer on the cathodic sites of the steel surface. And this layer often involves iron sulfide. And it acts as a barrier, and it slows down the rate at which those hydrogen ions can react with the metal. So the acid is reacting with this protective film rather than directly with the underlying steel.
So it's almost like a sacrificial layer.
In a way, yeah.
Protecting the good stuff underneath.
Exactly.
What are the main advantages? Disadvantages.
Some of the key advantages are that they tend to remain effective even at high temperatures. And they can provide protection over longer periods of exposure. They also tend to be less expensive than the organic inhibitors. However, they do have some significant drawbacks. Their effectiveness can decrease noticeably in HCl solutions that are stronger than about 17%. They can also react with hydrogen sulfide, which is often present in oil and gas wells, to form insoluble precipitates like arsenic sulfide. And another big concern is they can poison the catalysts that are used in oil refineries, things like platinum. And they can even release toxic arsine gas.
Oh, not good.
Not
a byproduct.
As a byproduct of the corrosion process. So there are some definite downsides.
It's kind of a trade-off there.
It is, There's always a balance.
All right, so what about organic corrosion inhibitors?
So organic inhibitors,
how do they work?
Are typically polar organic molecules. And they absorb onto the metal surface, forming this protective film. Essentially a physical barrier between the metal and the corrosive acid.
So they're physically blocking it?
They are, They're getting in the way. Many of them function as as cathodic polarizers, meaning that they hinder the movement of hydrogen ions towards the cathodic sites where they would normally react.
Right.
And these molecules often contain atoms like sulfur, oxygen, or nitrogen
Okay.
in their structure, which are attracted to the metal surface. So they kind of stick there.
Okay. And what are their,
Yeah.
pros and cons compared to the inorganic ones?
So on the plus side, organic inhibitors can generally be used even when hydrogen sulfide is present,
Okay.
without the risk of those sulfide precipitates.
Right.
They also don't tend to poison refinery catalysts.
Okay.
And they're often effective across a wider range of acid concentrations.
Okay.
However, a key disadvantage is that they can degrade chemically over time,
Okay.
especially at temperatures above around 200 degrees Fahrenheit.
So in really hot wells,
Yeah, in really hot wells.
they're not as effective.
They might not last as long, yeah. And they also tend to be more costly than inorganic inhibitors. So again, there's that balance.
That balance, right? Cost versus benefit.
Cost versus benefit, exactly.
All right, and then you mentioned these inhibitor aids.
Yeah.
What role do they play?
So inhibitor aids aren't corrosion inhibitors themselves,
Okay.
but they work to enhance the effectiveness
Okay.
of organic inhibitors,
Right.
particularly at higher temperatures where the organic inhibitors alone might start to break down.
Okay.
Some common examples are potassium iodide, cuprous iodide, cuprous chloride, and even formic acid.
Okay.
So adding these to organic inhibitor formulations
Yeah.
can really extend that temperature range where the inhibitor remains effective.
Makes sense. So it's like a booster.
A booster, yeah.
All right. So now, with all these different additives that we might be adding,
Right.
do they ever, interact in a negative way?
That's a very important consideration. Compatibility between different additives is absolutely crucial.
Okay.
So any additive that interferes with the corrosion inhibitor's ability to absorb onto the metal surface can potentially reduce its effectiveness.
Okay.
For example, surfactants, which we'll talk about more in detail later, they can form these tiny structures called micelles that might solubilize the inhibitor and make it less likely to stick to the metal.
Gotcha.
Inorganic salts and mutual solvents can also potentially hinder this absorption process.
Okay.
So ideally, if it's feasible, any additives that might negatively impact the inhibitor's performance should be used in a separate pre-flush or overflush, rather than being mixed directly into the acid solution.
So we keep them separate.
We keep them separate, yeah. We don't want them fighting with each other down there.
Okay, so how do we actually determine if a particular corrosion inhibitor is going to work effectively in a specific well environment?
So the standard approach is laboratory evaluation. And this typically involves taking a small sample of the metal that's going to be used in the well, what we call a metal coupon, and exposing it to the specific acid and corrosion inhibitor mixture. That's planned for the actual treatment. And this testing is usually done in a heated and pressurized vessel to simulate the downhole conditions as closely as possible.
Makes sense.
And then the amount of corrosion that occurs is carefully measured by weighing the coupon before and after the test.
Gotcha.
And the inhibitor's effectiveness is often expressed as the rate of metal loss per unit area per day. For example, pounds per square foot per day.
Right. So it's not just about the overall weight loss of that metal sample.
Right.
But you also mentioned...
It's also about pitting factor.
Right. And how that, how localized that is.
Exactly. Yeah, pitting is a major concern because those localized, potentially deep attacks on the metal can really weaken the pipe. And the pitting factor is essentially a ratio that compares the composition of any gas phase that's present, the pressure, even the presence of other additives in the fluid.
Okay, so it's really complex.
It's a complex system.
Okay.
Yeah.
So what's the essential takeaway, when it comes to selecting a corrosion inhibitor?
Some degree of metal loss is generally expected during an acidizing treatment. So the key is to determine what level of loss is acceptable without compromising the structural integrity of the well. A common benchmark is to aim for no more than about 0.002 pounds per square foot of metal loss.
Yeah.
provided that there's no significant pitting.
Okay.
In some situations, a slightly higher loss,
Uh-huh.
up to around 0.095 pounds per square foot,
Okay.
might be acceptable.
Okay.
But if those limits can't be met
Right.
with a particular inhibitor,
Mhm.
then you need a more effective one.
Okay.
And if cost becomes a factor,
Yeah.
sometimes adjustments can be made to the treatment design itself.
Okay, so how could we, what could we do?
Um, you could pre-cool the well tubing
Like,
with a water flush before the acid treatment.
uh-huh.
You could use a less aggressive acid, like formic acid, if the formation allows.
Uh-huh.
Or you could just minimize the overall time
Okay.
that the acid's in contact with the metal. So there are.
All right, let's dive in today. We're going deep on matrix stimulation.
Yeah, really interesting stuff.
It's a method for boosting a well's productivity. By injecting solvents into the formation to get rid of anything clogging things up near the wellbore.
Exactly. Unblock that near wellbore area so oil and gas can flow more freely.
And we'll be mainly focusing on matrix acidizing.
Right. That's using acids to dissolve those minerals blocking the flow.
Now, this isn't about fracturing the reservoir, just to be clear. It's more localized.
Yeah, think of it as cleaning the pipes right near the faucet, not a whole house replumbing.
Perfect analogy.
Mm-hmm.
And the injection happens below the pressure that would fracture the formation.
Exactly. Just focusing on that critical zone around the wellbore.
And while we're mostly on acidizing today, there are other matrix stimulation methods, right?
Oh, yeah, definitely. Like using organic solvents to tackle things like waxes and paraffins. We've talked about those in some of our other deep dives.
Right. But for today, it's acidizing.
Acidizing it is.
And the most common acids we're using are HCl, hydrochloric acid, for carbonates.
Yep, that's your limestone, your dolomites, those kinds of rocks.
And then there's the combo of HCl and HF, hydrofluoric acid, for silicates.
Yeah, that's what you need for your sandstones, the ones with all those clays and feldspars.
Now, just to give our listeners a sense of scale, where are these reactions actually happening? How far out from the wellbore?
Well, in sandstones, you're generally looking at reactions happening within about a foot of the wellbore.
Okay, so pretty close in.
Yeah, very localized. But
Yeah.
with carbonates, it can be a bit more extensive.
Oh, really? How so?
You might see acid reactions extending anywhere from just a few inches to maybe even 10 feet out from the wellbore.
Okay, interesting. So when would you actually use matrix acidizing? What kind of well is a good candidate?
Well, it's particularly useful when a well's underperforming because of damage near the wellbore. That's what we call a high skin factor.
The skin factor. That's a measure of how much resistance there is to flow near the wellbore.
Right. Exactly. It's like a clogged filter around your well, making it harder for the oil and gas to flow in.
Got it. So acidizing is like sending in the drain cleaner to clear that out.
Perfect analogy again.
But wouldn't you also use it on good wells sometimes?
Oh, yeah, absolutely. Even a good well, a high-producing one, can get a boost.
Really? How much of an improvement are we talking?
Even a 20% increase in flow can be a huge economic win if you're starting with a lot of production.
Wow, that makes sense. And I know you mentioned some carbonates might be special cases too.
Right, those naturally fractured carbonates or ones with lots of void spaces, those can see some really dramatic improvements.
How so?
Well, the acid can really travel through those existing pathways and open things up much more than you'd expect.
So the best case scenario with matrix acidizing is restoring the natural permeability of the near wellbore zone.
Exactly. Get that rock flowing like it did before any damage occurred.
And across the entire production interval.
Yeah, that's the goal, right? Remove that blockage across the whole area where the well is producing from.
But we have to be mindful of not causing new problems while we're down there.
Oh, absolutely. You don't want to create more damage than you fix.
Right. So how do we ensure this is all happening in a way that doesn't hurt future production?
Well, it's all about understanding how the acid interacts with the rock, both chemically and physically.
And we're not just talking about the rock itself, right? There's the fluids already in the reservoir too.
Right. The oil, gas, water, all that. Those interactions can get pretty complex.
Okay, so our sources point out a few key factors to consider when designing a treatment. First off, how does the acid even get to the mineral surface to react?
Well, that's a two-step process. You've got mass transfer, where the acid moves from the bulk fluid to the mineral surface. That can happen by convection, the flow of the fluid itself, or diffusion, the random movement of the molecules.
Okay, so it's got to travel to the surface first.
Exactly. Then, once it's there, you have the actual chemical reaction between the acid and the mineral.
And either one of those steps can be the bottleneck, right?
Yeah. Absolutely. Whichever one is slower will determine the overall dissolution rate.
So if the mass transfer is slow, it doesn't matter how fast the reaction is, the overall process is limited.
Exactly. It's like waiting for the delivery truck to bring the building materials. If that's slow, the construction's going to be slow no matter how fast the workers are.
Right. Makes sense.
Mm.
And then there's the issue of those dissolved minerals potentially reprecipitating, right?
Ah, yes. That's a big one, especially in sandstone formations.
Why is that?
Well, those reaction products, sometimes they solidify and clog up those tiny pore spaces in the rock.
Like cleaning the drain and then it just clogs up again.
Yeah, that's frustrating, right?
And then there's the acid reacting with the reservoir fluids themselves, not just the rock.
Oh, yeah, those interactions can throw a few wrenches in the works.
What kind of problems are we talking?
Well, the acid might change the rock's wettability, for example.
Well, wettability, what does that mean?
It's whether the rock's surface prefers to be in contact with oil or water. And that can affect how easily oil flows.
Makes sense.
And you could also get other minerals precipitating out or even nasty emulsions forming.
Emulsions, what are those?
Those are mixtures of oil and water that don't separate easily, and those can block flow.
So a lot of potential issues there. And then, of course, the rock formation itself isn't uniform.
No, not at all. You'll have variations in permeability and how easily fluids flow, and in how much damage there is in different zones.
So how do you make sure the acid actually treats the right areas?
That's where acid coverage comes in,
Meaning?
making sure the acid reaches all the damaged areas, not just flowing through the easiest paths.
Right, because it'll naturally go where it's easiest to flow.
Exactly. And sometimes that means using techniques like acid diversion.
To sort of force it into those less permeable zones that might be the most damaged?
Yep, redirect it where it's needed most.
Sounds like designing an effective treatment is quite the puzzle.
It is, and our sources mention some core design variables we can adjust, like the acid type and concentration, injection rate and volume, and different additives.
Lots of levers to pull.
Many ways to optimize the process, but it's all based on understanding the underlying science.
Okay, so let's get into that science. Starting with the basics, stoichiometry. What is that again?
So stoichiometry, it's essentially the accounting of chemical reactions. It tells us the exact ratios of how much of each substance reacts and how much product you get.
Like a recipe.
Exactly. You need the right proportions of ingredients.
So give us an example. Let's say we're using HCl to dissolve calcite.
Okay, so in that reaction, for every 1 molecule of calcite that dissolves, you need 2 molecules of HCl.
So a 1-to-2 ratio.
Right, and you get calcium chloride, CO2, and water as the products.
Makes sense. But I know things get a lot more complicated with HF and the silicate minerals.
Oh yeah, much more complex. With HF and silicates, you have multiple reactions happening.
Can you give us an example?
Sure. When HF reacts with quartz, the first product you get is silicon tetrafluoride. But then that silicon tetrafluoride can react with more HF to form fluosilicic acid.
So it's not just a single, simple reaction.
Nope. And on top of that, these fluosilicates, they can exist in different forms depending on the acid concentration.
Which then affects how much HF is actually consumed in the whole process.
Exactly. It's not a simple 1-to-2 ratio anymore.
So to deal with this complexity, our sources bring up the concept of dissolving power. Can you explain that?
Sure. Dissolving power is basically a measure of how good an acid is at dissolving a specific mineral. In practical terms, how much mineral can a certain amount of acid dissolve?
Okay, and there are two ways to express this, right? Gravimetric and volumetric.
Exactly. Gravimetric dissolving power, we symbolize that with the Greek letter beta. That tells us the mass of mineral dissolved per mass of acid.
So pounds of rock dissolved per pound of acid, for example.
Exactly. And you can calculate that using those stoichiometric coefficients we talked about, along with the molecular weights of the acid and mineral.
Okay, so that gives us a mass-based measure. What about the volumetric dissolving power?
That's represented by the letter X, and it tells us the volume of mineral dissolved per volume of acid.
So cubic feet of rock dissolved per cubic foot of acid, something like that.
Exactly. That's particularly useful in the field, where we usually measure and pump fluids by volume.
Right, makes sense. And our sources have some handy tables with these dissolving power values for various acid-mineral combinations.
Those are super helpful when you're planning a treatment. And then there's a great example in Sidebar 16a that shows how this all works in a real-world scenario.
Yeah, that one looks at dissolving albite, a type of feldspar. in a sandstone formation using a 3% HF solution.
Right. They calculate how much acid you'd need to dissolve a certain percentage of the albite within a specific radius around the wellbore.
So it takes that theoretical dissolving power and
Well,
shows how it translates into actual volumes of acid we pump.
exactly. It gives you a good ballpark estimate for a specific treatment goal.
So we know how much acid we might need. But equally important is how fast these reactions happen. Enter kinetics.
Kinetics, yes, all about the rates of reactions. How fast is that acid dissolving those minerals?
And as we touched on earlier, there are two main stages involved: getting the acid to the surface and then the actual reaction at the surface.
Right, and one of those will usually be the rate-limiting step.
The slower one dictates the overall speed.
Exactly. Like HCl reacting with calcite, that reaction itself is super fast.
So it's usually the transport of the HCl to the surface that's the bottleneck.
Precisely. But with HF and some of those sandstone minerals, the surface reaction itself can be slower.
So that limits the overall rate.
Right, and it's important to remember that surface reaction rate, it's not constant.
Depends on what?
Well, the acid concentration right there at the surface, the temperature, and also a factor called the reaction rate constant.
That constant reflects how inherently reactive the acid-mineral pair is, right?
Exactly. Some combinations are just naturally faster than others.
So how do scientists actually measure these reaction rates in the lab?
There are a few methods. One is using a stirred reactor where you have mineral particles suspended in the acid solution.
And you're constantly stirring it to ensure good mixing.
Right, so you minimize any mass transfer limitations, and then you track how the acid concentration changes over time.
Okay, and that tells you the reaction rate.
Another method uses a rotating disc made of the mineral.
And by rotating it, you control the flow of the acid over the surface.
Exactly, and that helps isolate the surface reaction rate.
Clever. And then you can also use core flood experiments, right?
Yes, where you pump acid through an actual core sample and measure how the permeability changes.
And then try to match those observations with computer models that incorporate different kinetic parameters.
Right, it's a more indirect way to get at the reaction rates.
Okay, let's talk specifics. HCl with carbonates, there's some important research by Lund and his colleagues on that.
Yes, they did some great work on the kinetics of HCl reacting with calcite and dolomite.
And they came up with equations to describe the reaction rate as a function of HCl concentration and temperature.
Right, really important for predicting how HCl will behave in a carbonate reservoir.
And those key parameters for their equations are all neatly summarized in a table in our sources.
That's very handy.
Now, what about those weaker acids, like acetic acid or formic acid? They still use the hydrogen ion, but they don't fully dissociate like HCl.
That's an important point. Because they only partially dissociate, the actual concentration of reactive hydrogen ions is lower.
But the kinetic equations for HCl can still be adapted for them, right?
Yes, by factoring in their dissociation constant, we can still estimate their reaction rates with carbonates.
Okay, that's good to know. Now, on to the more complex scenario. HF reacting with those sandstone minerals.
Ah, yes, quartz, feldspars, clays, all sorts of things reacting there.
So much more intricate than just HCl and calcite.
Definitely. And we have kinetic expressions for HF reacting with all those major sandstone minerals.
And generally, the rate is proportional to the HF concentration.
Right, we call that a first-order dependence.
And our notes mention that HCl can actually speed up the reaction between HF and feldspar, even though HCl itself isn't being consumed in that specific reaction.
Yes, it's like a catalyst boosting the rate.
And then there's the issue of reactive surface area, which is particularly relevant for the clays.
Right, the actual portion of the surface area that's accessible and reacting with the acid.
And for clays, that can be much smaller than their total surface area.
Exactly. Because of their microscopic structure, a lot of their surface area might be hidden away.
So even though they might have a slower reaction rate per unit of reactive surface area, their huge total surface area can still lead to a very high overall reaction rate.
Right, both factors matter. And sidebar 16b has a nice example that compares the reaction rates of quartz, albite, and montmorillonite.
It really highlights how the intrinsic reactivity and the available surface area both play a role.
Absolutely.
Okay, so dissolving those minerals sounds great for increasing permeability, but our sources keep bringing up the potential problem of precipitation.
Right, those reaction products coming out of solution and potentially clogging things up again.
And this is a bigger issue in sandstone acidizing than in carbonates.
Much bigger.
Why is that?
Well, in sandstones, you have more potential for forming those problematic precipitates.
Like what?
Well, calcium fluoride is a big one.
That forms when HF reacts with any calcite that might be present, right?
Exactly. And calcium fluoride is very insoluble, so it can really clog up those pores.
But you can mitigate that with an HCl pre-flush, right?
The HCl will dissolve the calcite first, so it's not there to react with the HF.
Okay, that makes sense.
Yeah.
What about colloidal silica? That seems like a tricky one.
Yeah, colloidal silica, those tiny silica particles, they can be a real problem.
And it seems like it's almost inevitable in sandstone acidizing.
Well, the spent acid, after reacting with those silicates, it's usually supersaturated with silica,
Hmm.
meaning there's a tendency for it to precipitate out as colloidal silica.
And the risk of that increases with temperature.
Right. Yes, unfortunately. So what you want to do is minimize the time that spent acid sits in the formation.
So inject at high rates to push the potential precipitation zone further out.
Exactly. And then flow back immediately after the treatment to remove that spent acid before it can cause too much trouble.
Okay, so rapid injection and immediate flowback for silica. What about ferric hydroxide?
Ah, yes, that one's a problem if you have iron present.
From the formation itself or maybe corrosion in the wellbore.
Both are possible sources. And if those ferric ions get in the spent acid, they can precipitate as ferric hydroxide when the pH rises.
And that can also plug up the pores.
Yes, it forms a sort of gelatinous precipitate.
And the solution there is sequestering agents.
Those can help keep the iron in solution, but you have to be careful with them.
Why is that?
Well, some research suggests those sequestering agents themselves can sometimes cause precipitation under certain conditions.
So it's a balancing act, and then there's the issue of asphaltene sludges, which are specific to certain crude oils.
Right, those heavy organic components in the oil can get destabilized by the acid and form a sticky sludge.
Not good.
No, definitely not. But luckily, you can often predict that with simple bottle tests.
So you know whether it's a concern beforehand.
Right, and if it is, there are ways to prevent it, like using emulsions of acid in aromatic solvents or special additives.
Okay, so we can anticipate and hopefully avoid those sludges. Now, what about predicting these precipitation problems in general? Our sources talk about using geochemical models.
Geochemical models, those are great tools. They use computer simulations to predict how the acid and the rock will interact.
And they can tell us which minerals will dissolve and which new solids might precipitate out.
Exactly. And you can even visualize it with time distance diagrams, like Figure 16.2 in our sources. It shows potential zones of silica and aluminum fluoride precipitation.
And you can couple those geochemical models with other models that predict permeability changes.
Right, so you can actually estimate the productivity improvement you'd expect from the treatment.
And there's a good example of this in Sidebar 16C, where they evaluate different acid formulations for a sandstone formation.
Yeah, they simulate the acid and mineral distribution, see where the HF gets consumed, and identify potential precipitation zones.
And by varying the HCl and HF concentrations, they can find the optimal mix for that particular sandstone.
Really powerful stuff.
So a lot of tools to help us predict and mitigate those precipitation risks. Now let's shift gears and focus on sandstone acidizing specifically. What's a typical treatment involve?
Well, usually you start with an HCl pre-flush, about 50 gallons per foot of the producing interval.
Okay, so that's to dissolve any calcite and prevent that calcium fluoride problem.
Exactly. Then you inject the main treatment, the HCl-HF mixture,
And how much of that do you typically use?
somewhere between 50 and 200 gallons per foot, depending on the specific formation.
And after that?
After that, a post-flush, usually diesel, brine, or more HCl, just to displace the HF away from the wellbore.
Okay, so it's a multi-stage process. And then it's crucial to flow back the well immediately.
Absolutely. Get that spent acid out before it can precipitate and cause more damage.
Now, our sources introduce a simplified model for understanding how HF reacts in sandstones, where they categorize the minerals as either fast-reacting or slow-reacting.
Right. It's a good way to conceptualize it, even though sandstones have many different minerals.
So the fast-reacting ones are things like feldspars and clays.
Yep, and the slow-reacting one is primarily quartz.
And then we get into some dimensionless variables and groups like the dam color number and the acid capacity number. What's the point of those?
Well, those dimensionless groups help us compare different acidizing scenarios without getting bogged down in specific units.
Okay, so they're like scaling factors.
Exactly. The dam Kohler number, for example, tells you how quickly the acid is reacting compared to how fast it's being transported.
So a high dam color number for those fast-reacting minerals means they're dissolving very rapidly right near the injection point.
Right. And the acid capacity number relates the amount of mineral that the acid could dissolve to how much is actually present.
Okay, that makes sense. And we're told that a reaction front is established as the HF reacts with those fast-reacting minerals.
Yes. And the shape of that front, whether it's sharp or more diffuse, depends on the dam color number.
So if the dam Kohler number is low, the reaction is slower relative to the transport, and you get a more spread out front.
Right. But if it's high, the reaction is very fast, and you get a sharp front where the HF is essentially consumed in a very narrow zone.
And there's a mathematical solution for situations where you have that sharp front.
Yes, you can use it to predict the position of the front and the HF concentration behind it.
And you can adapt that solution to different flow geometries like radial flow, linear flow, and even the flow around perforations.
Exactly. Table 16-6 in our sources shows how to define the variables for each case.
And there's a detailed example in sidebar 16D that compares radial flow and perforation flow for specific sandstone.
It shows how the acid penetration and skin reduction change with the volume of acid injected.
Really interesting stuff. But our sources do point out that this simplified two-mineral model has its limitations, especially at higher temperatures.
Right, because at high temperatures, you have to consider the reaction of fluosilicic acid, which is a byproduct of the initial HF reactions.
So it's not just HF reacting with the minerals anymore.
Nope, you've got this other acid in the mix now.
And that can change things significantly.
It can. It might mean you need less of the initially injected HF because the fluosilicic acid is helping dissolve those fast-reacting minerals.
But it also increases the risk of silica gel precipitation.
Right, so it's a trade-off.
And Sumatardo's work from 1995 compared this simpler model to a more complex one that includes fluosilicic acid.
And the results were quite different. The more complex model predicted much deeper dissolution of the fast-reacting mineral.
But also a significant zone of silica gel formation.
Right, so it's important to consider those secondary reactions, especially at higher temperatures.
And finally, when we're talking about sandstone acidizing, the ultimate goal is to improve permeability.
Absolutely. That's how we know the treatment is working.
But it sounds like the permeability response isn't always straightforward.
No, it can be quite complex with competing effects happening.
Like what?
Well, you have the dissolution of minerals creating larger pores, which increases permeability.
That's what we want.
Right, but you can also have those released particles getting lodged in the pore throats, reducing permeability.
Oh, great.
And of course, the precipitation of reaction products can also clog things up.
So it's a delicate balance.
It is. And if you have any carbonates in the sandstone, the CO2 generated during that initial HCl preflush can temporarily reduce permeability too.
So you might actually see a decrease in permeability initially before it starts to improve.
Exactly. It's not always a simple upward trend.
Okay, let's move on to carbonate acidizing now.
Mhm.
What are the key differences compared to sandstone acidizing?
The main difference is the type of rock and its solubility in HCl.
So carbonates are generally much more soluble in HCl than sandstones are.
Exactly. And if a rock has more than about 20% HCl-soluble minerals, which is typical for carbonates, you usually just use HCl alone, no HF needed.
Okay, simpler in that regard.
And the precipitation risks are also much lower with carbonates.
Why is that?
Well, the reaction products, mainly calcium chloride and CO2, they're much more soluble in water.
So less likely to form those damaging precipitates.
Right. You might get some temporary CO2 bubbles or some calcium chloride precipitation, but those tend to resolve themselves once the well is producing again.
Okay, so less worry about precipitation.
Yeah.
But modeling carbonate acidizing is still challenging, right?
Yes, because the reactions between HCl and carbonates are so fast, it's hard to capture that dynamic accurately.
And instead of a slow-moving reaction front, we get these things called wormholes.
Wormholes, yes, those are fascinating.
Tell us about them.
They're essentially highly conductive channels that the acid etches out in the carbonate rock.
And they can have incredibly high permeability compared to the surrounding rock.
Orders of magnitude higher. So the goal in carbonate acidizing is often to create and propagate these wormholes.
To bypass that near wellbore damage and connect the well to the more permeable parts of the reservoir.
Exactly.
And these wormholes, they have a really distinctive appearance, almost chaotic, but also kind of organized.
Right. They often exhibit fractal behavior.
Meaning what?
Meaning you see similar patterns repeating at different scales of magnification.
Oh, interesting. So it's like a self-similar structure.
Exactly. And that fractal nature has even been used to develop some empirical methods for designing treatments.
Okay, so given how complex this wormhole formation is, it seems like models are really important for guiding our treatments.
Absolutely. They help us figure out the best injection rates, acid concentrations, and whether to use any additives.
And our sources emphasize two key aspects: wormhole initiation and wormhole propagation. Let's start with initiation. How do those wormholes even get started?
Well, the fractal nature suggests that initiation is an ongoing process.
Not just a single event.
Right, it's happening continuously along the pore surfaces and at the tips of any growing channels.
And it's heavily influenced by the injection rate, the flux of acid into the rock.
Very much so. Too slow, and you just get uniform dissolution, no real wormholes forming.
And too fast.
Too fast, and you often get a lot of branching, a very inefficient wormhole structure.
So there's a sweet spot in between.
Exactly. An optimum rate that encourages the formation of a few dominant wormholes.
And understanding this flow rate dependence is key for interpreting those lab experiments and even predicting the optimal injection rate in the field.
Right. It gives us a starting point for designing treatments.
Now, the actual process of a wormhole, starting from a single pore, seems incredibly complex.
Oh, it is. You've got acid flowing, diffusing to the pore walls, and then reacting with the rock.
And the size and shape of those pores will also matter.
Absolutely. And some researchers have developed pore scale models to try and capture those details.
But those require a lot of detailed information about the rock, which isn't always available.
Right. It can be hard to get that level of detail in a real reservoir.
Now, there's also this concept of a critical pore size.
Yes, that's the idea that if the native pores are smaller than a certain size, wormhole initiation might not happen easily.
Because they need to enlarge a bit first.
Exactly. And the rate at which a pore grows depends on its length, the acid concentration, the flow velocity, and the reaction kinetics.
And by considering different scenarios, you can derive this critical pore size.
Right. And if most of the pores are smaller than that, you might need some initial dissolution before the wormholes can really take off.
Okay, so that critical pore size gives us an idea of whether we'll need some initial pore enlargement.
Exactly. And it's also related to the optimum acid flux for wormhole initiation.
So the best injection rate to get those wormholes started.
Right. And that optimum flux depends on the critical pore area, the reaction rate, and the acid concentration.
Now, what about those lab experiments? We see they use metal casts and pressure measurements to study wormholes.
Those are both valuable techniques. The metal casts, they give us a visual representation of the wormhole structure.
So you can see how the injection rate affects the pattern.
Exactly. Low rates, you get uniform dissolution. High rates, you get lots of branching. But there's an intermediate range where you get the most efficient wormhole propagation.
And that's what we want in the field, right?
Right, a few dominant wormholes that penetrate deep into the formation.
And those intermediate rates also tend to use the least amount of acid to achieve breakthrough, which is when the wormhole reaches the other end of the core.
Right, so you're minimizing the acid volume needed.
And the acid flux at the tip of those efficiently growing wormholes, it often matches the theoretical predictions based on that critical pore area concept.
Which shows that the theory is actually lining up with what we see in the lab.
That's good to know. And then there's the issue of fluid loss, which is a big factor in how far those wormholes will actually propagate.
Yes, as the wormhole grows longer, more acid is lost into the surrounding rock.
So the rate of propagation slows down.
Right, and that's something we need to consider when designing treatments.
So the takeaway seems to be start with a moderate injection rate to initiate those dominant wormholes, then maybe increase the rate later to help them extend further.
That's a good general approach.
Okay, what about temperature? How does that affect things?
Well, higher temperatures generally speed up the reaction between HCl and carbonates.
So the whole process happens faster.
Right. And that means the critical pore size for wormhole initiation also increases.
So you might need a higher injection rate at higher temperatures to get those wormholes going.
Exactly. Figure 1613 illustrates that concept nicely.
And once you're at or above that optimum rate, it's not as critical to maintain it exactly.
Right, but you definitely don't want to go too far below it.
Because then you'll use a lot more acid than necessary.
Exactly.
And finally, what about the composition of the carbonate rock itself? HCl reacts slower with dolomite than with calcite.
That's true. And because of that slower reaction, many of the pores in dolomite might already be larger than that critical size.
So you could end up with a lot of small, branched wormholes instead of a few dominant ones.
Right, not as efficient.
And figure 1614 shows that for dolomite, you generally want to use slower injection rates. especially in shallower formations.
Yeah, you want to give the acid time to etch out those dominant channels.
But in deeper, hotter dolomite, you might be able to increase the rate a bit because the higher temperature speeds up the reaction.
Right, so it's a balancing act again.
And sidebar 16E has a good example of calculating that optimum rate for a calcite formation at a specific temperature.
It shows how much the temperature can influence the optimal injection strategy.
So a lot to consider there. Now, we've talked about how wormholes get started, but how do they actually propagate?
Well, the rate at which a wormhole grows depends on how much live acid reaches the tip.
Makes sense. No acid, no etching.
Right, and that acid transport to the...
All right, diving in today, folks, and we're tackling a big one, a real cornerstone in the world of oil and gas. We're talking about acidizing carbonate rocks. And, you, our listeners, really came through. You sent in some awesome resources on this. There's this one chapter really dives deep into the design of these treatments. So today, we're on a mission, got to sift through all this, find those nuggets of gold, the most important, most interesting insights about this whole process. So first things first, let's break it down. What exactly are we dealing with when we talk about carbonate rocks?
Well, at the most basic level, carbonate rocks are all about their makeup. Over half of their composition has got to be carbonate minerals. And the real stars of the show here, the main players, are calcite, that's calcium carbonate, clay CO3 for your chemistry buffs, and then there's dolomite, a bit more of a complex character with both calcium and magnesium carbonate in the mix. That's KTU3 and MgCO3. So think of those as the fundamental building blocks of these rocks.
Okay, calcium and magnesium, the dynamic duo of the carbonate world.
Mhm.
Now, let's say you're a geologist, right? You got this rock sample in front of you. How do you tell if it's limestone or dolomite or somewhere in between? Is there like a special geologist taste test or something?
No taste tests required, thankfully. The main way we do it is by looking at that ratio, the balance between calcite and dolomite. If a carbonate rock has over 50% calcite, boom, we generally call it limestone. So it's really about the dominant ingredient, just like when you're following a recipe in the kitchen.
Makes sense. Now, flipping through your sources, one thing that jumped out was this idea that carbonate rocks, they're not just any old rocks, right? They've got some pretty unique characteristics. What sets them apart in the world of rocks?
Yeah, there are some really interesting features. Many of these rocks, they have what we call double porosity. Picture this, think of a sponge. You got those big cores, you can see them easy, but then there's this whole network of tiny interconnected pores within the sponge material itself. Some carbonates have a structure kind of like that. And then on top of that, they can have these really big differences in how easily fluids can flow through them. We're talking about high permeability contrasts, and sometimes, get this, even within the same rock formation. It's wild. These quirks, these unique traits, they're largely a result of how these rocks first formed, often from the remains of ancient marine life.
So they've got this intricate kind of hidden plumbing system, and it's not always consistent. Makes sense, right? That'd be super important to understand when you're trying to extract oil and gas. And the main tool for the job, from what I gathered, is hydrochloric acid, good old HCl. Why is that the go-to for acidizing?
There's a few solid reasons, actually. First off, HCl, it's really reactive with both calcite and dolomite, right? The main components we talked about. Plus, it's pretty easy to get a hold of and in the huge quantities you need for these field operations. And last but not least, it's pretty cost effective, especially compared to some other options out there. So you've got effectiveness, availability, and a reasonable price tag, all in one package. Can't really beat that, can you?
Makes perfect sense. Effective and economical. It's a winning combo for sure. Now, one thing your sources stress was that acidizing carbonates, it's a whole different ballgame than acidizing sandstones.
Yeah.
Can you break that down for us, explain that crucial difference?
Yeah, absolutely. So when you're acidizing sandstone, the goal is usually pretty straightforward. You're basically clearing the path, right? Getting rid of any blockage or damage that's preventing the oil or gas from flowing easily. Think of it like removing a clog in a pipe. But with carbonate acidizing, well, while we are also trying to bypass damage, we're actually dissolving the rock matrix itself. We're creating these brand new pathways, highly conductive channels for the fluids to flow through. So with sandstones, you're targeting the problem, you're fixing the pipe, so to speak. But with carbonates, you're actually modifying the rock itself to make it flow better. That means when you're designing an acid treatment for carbonates, you got to think about both the inherent nature of the rock, like what it's made of, how porous it is, and also, of course, any existing damage. It's a two-pronged approach.
All right, yeah, that's a really key distinction. Got to wrap our heads around that.
Yeah.
So let's rewind a bit. Go back to the beginning. Where do these carbonate rocks actually come from? They don't just magically appear underground, do they?
You're right, there's a whole history there. The majority of carbonate rocks, they actually have an organic origin. Think ancient seas, teeming with life. You've got everything from tiny plankton to larger creatures with shells. All those skeletons, they're mainly composed of calcium carbonate. Over millions and millions of years, these remains, they pile up on the ocean floor, forming the basis of what will eventually become carbonate sediments. There's also some chemical precipitation of calcium carbonate that happens, but the organic activity, those ancient life forms, they're the real stars of the show.
So we're basically talking about fossilized seashells, coral reefs, all that ancient marine life compressed and transformed over eons. Pretty mind-blowing when you think about it. Now, what about those initial characteristics, when these sediments are first formed? What about their porosity, the empty spaces, and their permeability, the ability of fluids to flow through?
All right, so these initial sediments, they're often made of fairly uniform, non-eroded material, which gives them a high initial porosity, meaning lots of gaps between the grains. But permeability, that's all about how connected those spaces are, how easily fluids can move through them, and that depends heavily on the size and shape of those grains. Take chalk, for example. It's made from the teeny tiny remains of microscopic organisms. It can have high porosity, lots of empty space, but the permeability can be really low because those pores are so small and not well connected. It's like trying to get through a maze with super narrow passages. Then you've got oolitic limestones made of these larger, rounder grains. They can have similar porosity to chalk, but way higher permeability because those pores are bigger and more interconnected. So you see, just having empty space doesn't guarantee easy flow. It's all about how those spaces are linked up.
So the size and shape of those grains, that's what dictates the permeability.
That makes a lot of sense. But rocks, they don't just sit there unchanging, right? They go through a lot of transformations over geological time. You mentioned diagenesis in your sources. Sounds pretty intense. What kind of post-depositional changes are we talking about here?
Yeah, diagenesis is basically an umbrella term. It encompasses all the chemical and physical changes that these sediments go through after they're first deposited. On the chemical side, you've got things like neomorphism, where the minerals tend to evolve into more stable forms like calcite and dolomite. Dolomite that often forms through long-term contact with magnesium-rich fluids. And here's a twist. Dolomitization can actually increase the porosity, create more space. But sometimes it can also mess with the permeability. It does this by precipitating these dolomite crystals, basically blocking the flow paths. It's like putting obstacles in the way of the fluid. And of course, you've got the opposite process. De-dolomitization happens when dolomite reacts with rainwater. It's like a constant game of mineral musical chairs down there. A mineral dance-off. I like that. Now, what about the physical side of diagenesis? What kind of pressures and stresses do these rocks experience deep underground?
Burial is the main culprit here. As these sediments get piled on by more and more layers above them, the pressure just keeps building. And that does some crazy stuff to the rock. It squeezes out those pore spaces, causing both porosity and permeability to decrease. If the pressure gets high enough, you can even get these minerals dissolving and then immediately reprecipitating, lining those existing pores, making it even harder for fluids to flow. And in some extreme cases where water is able to escape under all that pressure, you can even get dissolution and reprecipitation at the grain boundaries, leading to super low porosity, but also the formation of fractures or fissures. And these fissures, they become the main pathways for fluids to move through. So it can be a real transformation from a porous sediment to almost a solid rock, depending on the depth and those water conditions.
So from a sponge to a brick, basically, depending on the circumstances.
Yeah.
Pretty dramatic. And you mentioned that carbonates are more sensitive to these changes than sandstones. Why is that?
Think back to those initial sediments. Carbonates, especially stuff like chalky mud, they can be pretty fragile, not as tough as those sturdy quartz grains you find in sandstones. So if the water trapped between the grains is squeezed out during burial, a soft, chalky material at the surface can turn into this really dense, compact, calcitic rock, once it gets down to depths greater than, say, 6,500 feet. Sandstones, they tend to hold their shape better. They don't undergo such drastic changes. They're more resistant to all that pressure.
Makes sense. Copper grains, less drama.
Yeah.
You also brought up mechanical stress leading to fractures. How important are these fractures for actually getting oil and gas out of carbonate reservoirs?
Oh, they can be game changers. Absolutely crucial for making these reservoirs economically viable. tectonic forces, the earth moving and shifting, can create these massive networks of fractures throughout the rock. And sometimes these fractured reservoirs, they act kind of like they're homogeneous, with uniform porosity throughout, but their permeability, their ability to transmit fluids can be way, way higher than the permeability of the rock matrix itself, like orders of magnitude higher. These fractures, they're like the superhighways for hydrocarbons to travel to the wellbore. So sometimes it's those cracks, those natural imperfections that really make the
It's
difference.
all about the cracks. Fascinating stuff. Now, let's talk damage. What kind of damage can occur in carbonate formations? Is it the same stuff we see in sandstones, or there's some unique challenges?
For the most part, it's the usual suspects, the same culprits that cause trouble in sandstone reservoirs. You've got particles plugging up the pores, you've got mineral scale buildup, organic deposits, all that fun stuff. They can all wreak havoc in carbonates too. The one big exception is damage related to clay minerals, simply because carbonates, they generally don't have a lot of clay in their original makeup. So we usually don't have to worry as much about clay swelling or migration issues in these types of formations. One less headache to deal with.
So no clay dramas, that's a plus.
Mm.
But you did mention one specific vulnerability, something about poorly cemented chalks encountering acidic water-based fluids. What's the concern there?
Right, yeah, this is something to watch out for. So in some chalks, the stuff that holds the rock together, the mineral cement, it's not super strong. And if these chalks come into contact with acidic fluids, even if it's not a full-on acid treatment, that cement can start to dissolve. And if that happens, the whole formation can compact, squeezing out those pore spaces, and the permeability takes a nosedive, sometimes permanently. It's a real bummer. So choosing the right fluids, fluids that won't attack that cement, that's super important when you're dealing with these delicate formations.
Sounds like a delicate operation for sure. You also said that fluid surface tension, those water blocks, they're less of a worry in certain carbonate reservoirs. Which ones are we talking about, and why is that?
Yeah, so water blocks, they tend to be less of an issue in fractured reservoirs, specifically the ones with low permeability in the rock matrix itself. The reason is pretty simple. Any damage caused by drilling fluids or completion fluids, it tends to concentrate in those natural fractures, those larger flow paths. And because the rock matrix itself is already pretty tight, fluids don't move through it easily anyway. So the issue of water getting stuck in those tiny matrix pores, it's just not as big of a deal compared to a more permeable, homogeneous reservoir. The main problem is in those larger cracks, the fractures, where we want the flow to happen, and that's where we focus our attention.
So the damage is already focused where we need to address it. Makes sense. And what about those crucial fissures, those natural fractures? What kind of specific damage problems can they run into?
Well, fissures, they're kind of fickle. Because they experience these pressure changes during production or injection, they can be prone to mineral scale buildup. Basically, various inorganic compounds, they decide to settle down on the fracture walls, blocking those flow paths. And sometimes changes in pressure and temperature can cause heavier hydrocarbon components, like asphaltenes, to precipitate out within the fissures. It's like these pathways are getting clogged up over time, so keeping those fissures open and flowing, that's a major challenge in a lot of cases.
So it's a constant battle, keeping those pathways open. All right, let's bring it back to our main weapon, hydrochloric acid. We talked about why it's the top choice, but how do we actually put it to work down there? What we're trying to achieve with these acidizing treatments?
When you're acidizing a carbonate formation with HCl, you've got two primary goals. One, you want to bypass any existing damage, clear a path for the hydrocarbons to flow. And you do that by creating these high conductivity channels. We call them wormholes. They're like these tunnels that the acid etches out of the rock. And two, you want to open up those natural fractures, make them wider and more effective conduits for flow, especially in low permeability fractured reservoirs. So basically, you're creating new pathways or enhancing existing ones to get that oil and gas moving.
Wormholes. That sounds kind of sci-fi, but I'm guessing they're a good thing in this context. And you mentioned this term negative skin effect, which seems to be the target in carbon acidizing, unlike sandstone acidizing, where you're aiming for zero skin. Can you explain that?
Absolutely. So a negative skin effect basically means we're not just fixing the damage, we're making the well flow even better than it did originally. It's like giving it a super boost. And we can achieve that because the acid, it doesn't just remove the damage, it also reopens those natural fractures and creates this interconnected network of highly permeable wormholes, giving the hydrocarbons a much easier route to the wellbore. In sandstone acidizing, the goal is usually to restore the formation to its original state, hence the target of zero skin effect. But in carbonates, we often want to go beyond that, make it flow even better than nature intended.
So carbonates, it's all about exceeding expectations, really optimizing that flow. Now, you mentioned retarding the acid using emulsions or microemulsions. Why would we want to slow down such a reactive acid? Seems counterintuitive.
It's a control thing, really. Sometimes you don't want the acid to just go crazy and eat away at the rock too quickly. That's especially true in formations that are a bit weaker or less well cemented. If the acid reacts too fast, you can get what's called rock deconsolidation. Instead of creating a few dominant wormholes near the wellbore, a retarded acid tends to produce a more even, uniform increase in pore size throughout the treated zone. That helps to maintain the rock's integrity, prevents it from collapsing. Plus, by slowing down the reaction, by reducing that immediate contact area between the acid and the rock, you allow the live acid to penetrate deeper into the formation before it's all spent. It's like extending the reach of the treatment.
So it's about getting the acid to the right place and having it work its magic in a controlled manner. Really fascinating stuff. Now let's step back in time for a moment, explore the origins of this whole acidizing business. Your sources mentioned it goes all the way back to 1895. That's over a century ago. What were those early acidizing treatments like?
Yeah, the early days were definitely a bit more experimental, let's say. The first documented use of acidizing was in 1895 with a patent granted to a guy named Hermann Frasch the following year. His big idea was pretty straightforward. Just inject HCl into limestone formations, create those flow channels, try to boost production. The interesting part is Frasch didn't really consider using corrosion inhibitors back then, so to prevent the acid from literally eating through his well bore, he had to use special pipes lined with rubber or some other acid-resistant material. Pretty bold, if a bit risky, don't you think?
No corrosion inhibitors. Wow. That sounds, risky is an understatement. I can only imagine the headaches that must have caused. And you mentioned a decline in acidizing not long after. Was corrosion the main reason for that?
Most likely, yeah. While those early treatments, they did see some impressive initial results, that lack of proper corrosion control, it would have been a huge practical hurdle, not to mention a safety hazard. So it's pretty safe to say those issues played a big role in the decline of acidizing in those early years. The technology just wasn't quite there yet. They needed a way to tame that acid.
Fast forward about 30 years, and your sources mention the Gypsy Oil Company experimenting with inhibited acid in sandstone formations.
Yeah.
What were they up to, and how did that turn out?
So around the 1920s, Gypsy Oil, they were dealing with gyp deposits, basically calcium sulfate scale, in their sandstone wells. And they thought, hey, maybe we can use inhibited HCl to get rid of that stuff. The inhibitor they tried was actually the same type used in the steel industry for cleaning metals. But unfortunately, the results weren't all that impressive, and they didn't even bother patenting the process. So not exactly a groundbreaking moment for acidizing, more like a footnote in the history books.
A failed experiment, but hey, you learn from those, right?
Yeah.
But then came 1932, and it sounds like that's when the real breakthrough for acidizing happened thanks to Dow Chemical. What changed the game that year?
February 11th, 1932. Mark it on your calendars, folks, because that was a pivotal day for the oil and gas industry. Dow Chemical, they did something pretty remarkable. They took 500 gallons of HCl, but this time it contained a new type of corrosion inhibitor, an arsenic-based one, and they pumped it into a well drilled in a limestone formation. This was the first documented successful use of inhibited acid on a carbonate reservoir. And the result, well, let's just say it was a dramatic success. This well, which had been totally unproductive before, suddenly started pumping out a respectable 16 barrels of oil per day. That's when the industry realized, hey, this inhibited acid thing, it's got real potential. We can actually use this to boost production in a big way.
Talk about a turnaround. From zero to hero in a matter of days. And the crazy thing is, you said their initial goal was just to dispose of excess HCl. What a wild origin story for such a crucial technology.
Exactly. They were basically looking for a practical way to get rid of all that leftover acid from their chemical plants. But, as they were pumping this stuff into these disposal wells, they noticed something interesting. Those wells started accepting fluid at an increasing rate. And that sparked a light bulb moment. They realized, hey, if this is making those wells flow better, maybe we can use it to stimulate production in actual oil wells, too. And that's exactly what they did, first with brine wells at their own facility, and then, boom, the rest is history. A classic case of turning lemons into lemonade, or in this case, waste acid into a production bonanza.
From trash to treasure, that's a fantastic story. And Dow's, they didn't waste any time capitalizing on this discovery, did they? They quickly formed Dowell, Inc., to really push this new technology.
You bet they did. The potential was clear as day. And Dow, they were smart cookies. They formed the Dow Well Service Group, which then quickly became a standalone company, Dowell Inc., all within the same year, 1932. And of course, other service companies, they saw what was happening and jumped on the bandwagon. Within a few short years, acidizing was everywhere. It was the hottest new technology in the oil patch, and it all stemmed from this accidental discovery.
It's amazing how quickly things can change when there's a big breakthrough. And you also mentioned something pretty interesting about those very first hydraulic fracturing treatments, possibly involving acid, even before the concept of fracking was really understood.
Right, yeah. That's a little known piece of history that I find fascinating. Back in the early days, when they were trying to acidize those tight carbonate formations, they often ran into a problem. The wells just wouldn't accept the injected fluids, including the acid, until they hit a certain pressure. But once that pressure was overcome, the fluid would suddenly flow in very easily at a much higher rate. And what they later realized was that this sudden change, that pressure buildup followed by easy injection, it was probably caused by the acid actually fracturing the formation. Basically, they were inadvertently doing what we now know as acid fracturing. And because they didn't really understand what was happening at the time, later patents for hydraulic fracturing, the fracking we know today, they weren't really enforced against those early acid fracturing treatments. It's like acidizing was this unsuspecting pioneer, laying the groundwork for the fracking revolution that would come later.
It's funny how those early innovations can pave the way for future technologies in such unexpected ways.
Yeah.
Now let's get back to basics, the nitty-gritty chemistry of all this. How does HCl actually react with those key carbonate minerals, calcite and dolomite, at the molecular level?
Okay, so at its core, it's a classic acid-base reaction. You've got your acid, HCl, and your bases, calcite and dolomite. When calcite, which is calcium carbonate, KCO3, meets HCl, they get together and produce calcium chloride, KCl2, water, H2O, and carbon dioxide gas, CO2. It's like a chemical party, and these are the byproducts. Now, for dolomite, which is a bit more complex, it's got both calcium and magnesium carbonate, CamGCO32. The reaction is similar, but it uses up more HCl and produces both calcium chloride and magnesium chloride, MgCl2, along with water and twice the amount of CO2. So basically, you're dissolving the rock and releasing carbon dioxide gas as a byproduct. It's like a fizzy geological cocktail.
A rock-dissolving, gas-releasing party. Got it. And what happens to those byproduct salts, the calcium chloride and magnesium chloride? Do they cause any trouble downhole? Like, could they precipitate out and clog up the formation again?
Luckily, no. Both calcium chloride and magnesium chloride, they're really soluble in that spent acid solution. That means they tend to stay dissolved. They don't really have a tendency to come out of solution and cause more damage. Your sources actually had a handy table, table 17:1, which breaks down exactly how much of these byproducts are produced when you react a typical 15% HCl solution with limestone. And the numbers show that the spent acid can hold a lot of those salts. That's a big plus for using HCl. It doesn't leave behind a lot of messy residue.
Cleanup is easy. It's always a good thing. Now let's talk about the speed of this reaction. Your sources mentioned something called the reaction rate, Ka to R, which depends on the temperature and how concentrated that HCl is. How does that all work?
Right, so the reaction rate, it's basically how fast the acid dissolves the rock surface, and it's influenced by both temperature and acid strength. There's a general equation that describes this relationship. It's Kr equals Kr, where Kr is the reaction rate constant, C is the concentration of HCl, and N is the reaction order. Now, those values, Kr and N, they've been determined experimentally, and as you mentioned, Kr changes with temperature. The hotter it is, the faster the reaction, and for dolomite, that reaction order N, it can actually change with temperature too, which makes things a bit more complex.
So hotter temperature, stronger acid, faster reaction. Makes sense. But your sources pointed out something really interesting, that the reaction between limestone and HCl is so incredibly fast, it's actually tough to measure accurately at room temperature.
It's true. Limestone is a speed demon when it comes to reacting with HCl, especially at surface temperatures. It happens so fast, it's hard to track. Researchers, to study this, they had to get creative. They actually had to conduct their experiments at super low temperatures, like down to negative 12 degrees C, just to slow the reaction down enough to be able to measure it accurately. Dolomite, on the other hand, it's a bit more laid back. Its reaction is much slower, so you can measure it at higher temperatures, more like what you'd find in a reservoir. This difference in reactivity between the two, it's a key factor to consider when designing acidizing treatments.
So limestone, fast and furious, dolomite, slow and steady. Got it. Now, what about those weaker organic acids like formic acid and acetic acid? They can also react with carbonates, right?
Yeah.
But when would we ever choose those over the mighty HCl?
Yeah, organic acids, they can do the job, but there's a catch. When they react with carbonates, they produce a lot of carbon dioxide gas. And that CO2, it can actually build up at the rock surface and stop the reaction from going all the way, even if there's plenty of fresh acid around. It's a matter of equilibrium, a balance between the reactants and the products. The CO2 buildup, it's like putting the brakes on the whole dissolution process. Now, the main reason you might choose organic acids is if you're dealing with really high temperatures downhole, like above 400 degrees ARA, around 205 degrees C. At those temperatures, it gets really tough to prevent HCl from corroding those steel wellbore components, even with inhibitors. Acetic acid, it's generally preferred for those high temperature jobs because it's a bit easier to keep under control corrosion-wise.
So organic acids, they're the high temperature specialists that cool customers in extreme environments. But are there any other perks to using them besides that corrosion control aspect?
Well, acetic acid, it has this neat trick up its sleeve. It can actually help prevent the precipitation of ferric hydroxide, which is a byproduct you don't really want forming downhole, especially if there's iron present in the formation or the fluids. Acetic acid does this by forming a weak complex with the iron, basically making it harder for the ferric hydroxide to precipitate out. It's like a bodyguard for your wellbore. This is especially beneficial at lower temperatures, below around 125 degrees Fahrenheit. Now, another thing about organic acids, they tend to react in a more uniform way with the rock compared to HCl, which means they don't create those highly focused wormholes we talked about. This can be a good thing in some situations, like when you're dealing with a weaker formation that might not handle those large wormholes very well. But remember, they're not as strong as HCl, so you usually got to pump more of it to dissolve the same amount of rock. And they're generally pricier too, so you got to weigh the pros and cons. It's a balancing act, as with most things in life.
So it's all about choosing the right tool for the job, considering the temperature, the potential for byproducts, the rock strength, and of course the cost. Now let's geek out a bit about the physics behind all this, because it's not just about the chemical reactions themselves, right? There's this whole aspect of how the acid actually gets to the rock surface and how those dissolved products are carried away. Your sources called it acidizing physics.
Yeah, that's a good way to put it. When you zoom in on that reaction between HCl and a carbonate mineral, it's actually a multi-step process. First, you got to get those reactive components of the acid, those hydronium ions. They got to travel from the bulk fluid to the rock surface. That's step one. Then the reaction happens, the acid eats away at the rock. And finally, all those products of the reaction, like calcium and magnesium ions, CO2 gas, they got to move away from the rock surface back into the bulk fluid. So it's like a three-part dance. And the slowest of those steps, that's what dictates the overall speed of the whole process. We call that the rate limiting step.
And that rate limiting step, it can actually change depending on the conditions, right? Your sources said that for calcite reacting with HCl at room temperature or higher, it's usually transport limited. But for dolomite, it can switch from reaction rate limited to diffusion rate limited as you crank up the heat. What does that mean in practice?
So if a reaction is transport limited, it means the rate at which the acid can actually reach the rock surface. That's the bottleneck. Even if the chemical reaction itself is super fast, if the acid can't get there quickly enough, the whole thing slows down. Diffusion, that's the main mechanism for this transport. Basically, the acid spreading out from areas of high concentration to low concentration. Now, with dolomite, things get a bit trickier. At lower temperatures, the chemical reaction itself is the slowpoke. It's what limits the rate. But as you heat things up, that reaction speeds up, and suddenly the transport of fresh acid to the dolomite surface, that becomes the bottleneck. It's like a relay race, and the slowest runner dictates the overall time. Interestingly, some researchers have argued that if you zoom in really close, down to the level of individual pores, the chemical reaction rate might actually always be a big factor in how fast the acid gets used up. So the scale at which you're looking at things can change your perspective on which step is really in control.
So it's a complex interplay between acid delivery and reaction speed. Really cool stuff. Now let's talk about those wormholes. These are those macroscopic, high conductivity channels that form in limestone cores when you acidize them with HCl. What causes them to form, and what factors influence their growth?
Wormholes, yeah, they're fascinating. They form because of an inherent instability in the acidizing process. Imagine you have a bunch of pores in the rock. Some are a bit bigger than others. Maybe some have a slightly higher permeability. These more favorable paths, they're going to get a bit more acid flowing through them. And because they get more acid, they dissolve faster. They get even bigger and more permeable. It's like a positive feedback loop. The bigger pores attract even more acid, leading to even faster dissolution. Over time, this concentrates the flow into these dominant channels, creating those characteristic wormhole structures. It's like a self-organized process of channel formation.
Like the formation of superhighways within the rock. That's a great analogy. And you mentioned that the acid injection rate, how fast we pump it in, that plays a big role in how these wormholes develop. How does that work?
Right, so if you inject the acid too slowly below a certain critical flow rate, wormholing doesn't happen. You just get a more uniform dissolution of the rock surface.
Hmm.
But once you exceed that critical rate, boom, the instability kicks in and those wormholes start to form. Now, near that threshold rate, you'll often see one dominant wormhole forming, nice and thick. But as you crank up the injection rate even more, you tend to get a network of thinner, more branched wormholes instead. It's like switching from building one big tunnel to creating a more complex, interconnected system of smaller tunnels.
So slow and steady for a single channel, fast and furious for a network. That makes a lot of sense. And I know researchers have used computer simulations to study this wormholing phenomenon. What have they learned from those models?
Computer simulations have been super helpful, yeah. They basically create a virtual representation of the rock, like a simplified 2D or 3D network of interconnected channels. And then they can simulate how the acid flows through this network using the basic laws of fluid mechanics. And they include rules that dictate how each individual pore grows as it's exposed to the acid. These models are actually based on earlier, more simplified mathematical models that looked at acidizing in just one dimension. The great thing about these simulations is that they allow researchers to explore a much wider range of parameters than you could ever test in a lab. And what they've shown is that this unstable dissolution process, it's a real thing. It clearly leads to the formation of those characteristic wormhole patterns.
So computers have helped us visualize and understand those complex dynamics. Now, your sources mentioned this term fractal behavior in relation to wormholes. That sounds pretty intricate. What does that mean?
Yeah, it gets a little technical, but basically those wormhole patterns, they can exhibit fractal characteristics, meaning they display a degree of self-similarity at different scales. It's like a pattern within a pattern within a pattern. And this fractal behavior, it emerges between two extremes. At very low injection rates, where diffusion is the dominant mechanism, the acid tends to react quickly near the pore entrances and it doesn't penetrate very far. You end up with a more uniform but limited dissolution. At the other extreme, very high injection rates, the acid flows so fast that the reaction at the rock surface becomes the limiting factor. So you get a more uniform etching of the surface, but not much depth. The wormholing regime, where you get those branching patterns, it happens in that sweet spot between these two extremes. Your sources have a figure 17 to 1, which visually depicts these different dissolution regimes. It's worth checking out.
A visual aid is always helpful. Now, how do we actually quantify this transition from uniform dissolution to wormholing? Your sources mentioned the Pecklet number
Yeah.
and the Kohler number. What can those tell us?
Those are basically dimensionless numbers, like ratios,
Yeah.
that help us understand the relative importance of different processes happening during acidizing. The Pecklet number, it compares the rate of convective transport, that's the acid being carried along by the bulk flow, to the rate of diffusive transport, that's the acid spreading out due to concentration gradients. Now, for those reactions that are mainly transport limited, like calcite with HCl at higher temperatures, a higher Pecklet number generally means you're more likely to get wormholes. A low Pecklet number,